Welcome to Jamovi. Jamovi is an application for analyzing data and helping you make sense of the information around you. It's also a compelling alternative to expensive proprietary programs like SPSS and SAS and Stata. Instead, Jamovi is based on the open source programming language R, which is designed for working with data. And what that means is that Jamovi is free, it's open, and it's extraordinarily friendly. In fact, once you start using Jamovi, you'll simply be embarrassed that you didn't start using it sooner. Now, I want to mention one thing about this course. This is a tools course. I'm teaching you how to use software. It works best if you already know a little about data because I'm not going to be discussing the principles at great length. On the other hand, it's easier to learn data when you have a good tool like Jamovi. So really, either way works fine. Just get started and see what you can do. Go to jamovi.org and download the program, and then go to datalab.cc/tools/Jamovi to download all the course files so you can follow along with what we're doing and start working in your own data too. And with that, let's go. The first thing you need to do to work with Jamovi is to get it installed on your computer. It's a desktop application, so you'll need to have either Windows, Mac, or Linux, and you install it and run it locally. Go to jamovi.org and then simply click on this link, Download. Now, the beautiful thing is it's free and it's open source. Click the system that you need, Windows, Mac OS, or Linux. Download the file, double-click on it, and you'll be ready to start working in Jamovi in just a few seconds. When you open Jamovi, this is the window that you're going to see. Now, if you're used to some other applications like SPSS or SAS, what's a little different here is that it's a single window. Actually, that makes it really easy to organize and to navigate through it. But I want to show you a few different parts of what's going on. Now, over here on the left, of course, where we have rows and columns arranged in a grid, this is where your data goes. It's your data window. Right now, we have three variables just called A, B, and C. You're, of course, going to replace those with something else, and you put the data in. So it's one column per variable, one row per case. Over here on the right is the output window. It's where we'll see the results of our analyses. Up at the top, we have two tabs here. The first one that's open by default is Analyses, which gives you options for exploration. If I click on that and come to descriptives, you'll see, for instance, it opens up the menu that allows you to choose what you want to do, and you get a blank version of the results over here on the right. By the way, you'll notice that the menus in Jamovi are designed to resemble those of SPSS. It's not based on SPSS. Jamovi actually runs on R, but it's designed to make it easy for people who are used to SPSS to really migrate over to Jamovi. You can close the windows by clicking on this arrow, hide the options. And we have versions of t-tests, the analysis of variance or ANOVA or ANOVA, regression, frequencies, and then factor. And obviously, I'll go over each of these procedures in separate videos. You also have a data tab right here that allows you to paste in your information, to do a setup of the variables where you define what's in them. The type, it calls them continuous, although I would call that measured or scaled or quantitative. Ordinal or nominal, and then you can put down integer, decimal, or text. You can give levels, you can give names. You can compute new variables. You can add or delete variables in columns. You can filter your cases and add or delete rows for cases. I can hide this right here. At the far left, the three horizontal lines give you the menu to new, open, save, and so on, as well as recent data you have at the bottom. And then one more that's really important is way over here at the right. Click on the three dots, and you get a number of options, zooming and the number format. One interesting one here is the plot theme. So when it makes the graphs, if you really want it to look like SPSS, you can get the beige charts. I don't like them. I actually prefer minimal. Hadley is a reference to Hadley Wickham, the person who developed ggplot2, a very common graphics program for R users. And then minimal is also really nice. I'll keep it at default for now. And then syntax mode. If you click on this, then you're actually going to be able to see the R language syntax using the JMV package that allows you to duplicate any of these features, any of these analyses in R. That's an enormous benefit, especially if you're familiar with SPSS, but you're trying to learn R. And so that's a general orientation of what's going on in Jamovi. In the future videos, I'll show you how each of these options work, each of the analyses function, and how to read some of the output that you get from Jamovi. The fastest way to get started with Jamovi is to explore its example datasets. To do that, come up to the little menu, the three horizontal lines here, and come down to Open. Now, this PC means the ones that are installed on your computer, but examples, there are 4 sample datasets. The first one consists of Big 5 data. This is Big 5 personality characteristics. I'll click on that and it opens up. And what it has is 5 variables on the personality characteristics: neuroticism, extroversion, openness to experience, agreeableness, and conscientiousness. And they're rated on 1 to 5 scales. And this is a great data set for doing correlations, for doing regression, and for doing data exploration. Another good data set, again to open and examples, is tooth growth. Now, this is kind of a funny data set because it has to do with the length of teeth in guinea pigs. But what it has is a single outcome variable that's called len, that's for length, and then sup is for the supplement. This is an experiment where they are giving the guinea pigs one of 2 different supplements to aid in their tooth growth. It's either VC, which is for a vitamin C, or it's OJ for orange juice. And then on top of that, they manipulate the dosage, either 500, 1000, or 2000. And this allows you to look at the combined effect of these 2 factors on the growth of teeth in guinea pigs. It's a good way to get started with the analysis of variance. After that, there's bugs. This is a peculiar data set because it has to do with how people react to insects. We have a subject number, gender, male and female, region, some education, and then these 4 mysterious variables are the level of disgustingness and the level of frighteningness, either low or high on the both of them. And what this is a good example of the analysis of variance for a repeated measures or within subject variation, because everybody in this experiment gave responses to all 4 possible categories. And the final data set, under, again, examples, is the classic Anderson's iris data, also known as Fisher's iris data. And what this is the measurement of the sepal length and sepal width and petal length and petal width of 3 species of irises. So you have 4 quantitative or continuous variables and 1 nominal or categorical variable. This is a classic data set on how quantitative measurements can be used to place observations into categories. It's also a great way to practice breaking down explorations by groups because these species of iris differ pretty substantially in some of these measurements. And so use any of these 4 data sets as a way to start exploring how you can work with Jamovi. You'll see how quick and easy you can get into the data, get the exploration, start doing some analyses, and start getting some meaning out of the data that you have in Jamovi. One of the things I truly love about Jamovi is how easy it makes it to collaborate with other people. And the reason it's easy is because when you share things with people, you're sharing a single file. So for example, here's a potential analysis that I might do when I'm working with somebody. I've got a data set here. I've got the variables that came with the data set. I've got a calculated variable right here. You see the formula. I've got a descriptive analysis. Let me scoot this over a little bit. I've got descriptive statistics. I've got tables. I've got charts and box plots and all of this. And it's saved in a single file. So let me show you this, for example. All of this is saved in a single file that I've got called sharingfiles.omv, where .omv is the Jamovi extension. When I work with somebody, I do the analysis and then I send them this single file. and I tell them, download Jamovi, double click on this, and you'll open up right to where we were. And they'll have all of the data, all of the calculations, all of the transformations, all of the analyses. They'll have everything in one self-contained unit. And that is one of the easiest ways to share things. You can email the file to them. You can put it in a shared folder like Google Drive or Dropbox or Box. But any way you do it, the unitary nature of the files and the fact that they have all the work that you've done in there makes it extremely easy to collaborate and share work. Jamovi makes it easy to share files by simply emailing or putting in a shared box the file that you've been working on, because it has the data, it has the transformation, it has the analyses. There is, however, a really interesting, more sophisticated alternative to that, and it's called the Open Science Framework. And if you want to go here to osf.io, I can show you a little bit about how it works and how Jamovi is very well adapted to it. The Open Science Framework is a free service that really facilitates collaboration and reproducibility in research. You can create a free account, and one of the important things here is that it allows you to integrate a number of other services. So for instance, maybe you use Dropbox or Google Drive or Box. It can bring files in from those. Or if you're the programmer type, you might use GitHub or Amazon Web Services. Again, those are integrated. Now, I personally like to upload files one by one into OSF. That way I have a better sense of what's there. I don't put something in a folder by accident. But this is a way to share your work both with specific other people for collaboration and to share your results with the world. I want to show you how this works by having you go to an example. If you go to this web address, bit.ly/Jamovi-OSF for Open Science Framework, then you'll see the page that I created for these Jamovi tutorials. For that address, it's a shortcut and it takes you to this page in OSF. I've set up a read-only access to my files here, so anybody can look at it. They can see what's there. They can't change it, but this is a great way of collaborating. And right now I've got the files from the first chapter on the Jamovi course, and one of them is sharingfiles.omv. Now you may remember what this looks like in Jamovi itself. Right here, we've got the IRIS example data, and I've got some charts that are broken down by categories. I got some statistics. Let me show you what those look like when we're in OSF. If you click on this file right here, it's going to open up in your browser. I've got it open already, so I'm just going to move over. And here what you have is an exact reproduction of the results that we have. We have the same table. It looks exactly the same. And we push it down a little bit. We have the same charts, and it's all there. And in fact, even though people can't modify it, they can download it. And then they can open it themselves in Jamovi and start working with the data and see what they can get out of it. And so this is a wonderful way of collaborating and sharing results with people. And Jamovi is one of the few programs that opens its files natively in OSF that makes it so easy to share. One other thing I want to point out is, because this is just a web page, not only does it work on a browser like a Mac, Windows, or a Chromebook, it even works on smartphones. You can open it on an iPhone or an Android or a tablet, and you'll get the same results, and you can explore and share the results that way. So if you want to have a step up in your collaboration and in your sharing, and really a way of disseminating your research, OSF, the Open Science Framework, can be an excellent alternative that works so well with Jamovi. The base functions that come with Jamovi are really powerful and truthfully are probably enough to get you all the way through whatever it is you need to do. On the other hand, Jamovi is based on R, the statistical programming language, which has about 10,000 packages available that give extra functionality to R. And it turns out you can do a similar thing with Jamovi through what are called modules. Modules are to Jamovi what packages are to R or to Python. They give you extra functionality. So for example, if you open up Jamovi modules.omv, you'll see that I have the standard correlation matrix right here. You can click on this, and then you'll see the commands that come under regression. That's where they come from right here. And I'm looking at the sepal length and the sepal width of the IRIS data set. And we've got the correlations here, the p-value, and we've got a scatter plot. It goes down in this one corner. It's actually built for doing a matrix where you have many variables. But, we get some cool stuff. We get the regression line. We get the standard errors around it. We get density plots for the two variables, and we get the correlation written up here in small corners. But there's a module that allows you to do more than that. If you come up to modules and down to Jamovi library, what you'll find is there's about a dozen modules that are currently available. And the Jamovi developers are making a strong push for R developers to convert their R packages into Jamovi modules. They have instructions on how to do that on their website. And once they're available, you can sideload them, which means you download them separately and then import them into Jamovi. But it's best if they're available through the Jamovi library. We've got one on power analysis, general analyses for linear models. We have method selection. We've got meta-analysis. Scatter is a great one for doing plots. Toaster to one-sided test. Base R, this replicates the statistical analyses that are available in the base package in R. We have mediation and moderation. Walrus is a collection of robust statistics developed by Rand Wilcox. And we have survival analysis called Deathwatch, and even a little video game here called Jamovi Arcade. All you have to do is click on install and it'll put it in there, and then it'll be listed here under installed. Everybody gets this one, Jamovi. That's the default. I've added scatter, and let me show you what it looks like, why you would want to use one of these extra packages. This is the default version of the scatter plot matrix. I'm going to close the thing here by clicking on the side. But here's the one that I made using the scatter module. And you can tell, among other things, it's a lot prettier. It's got more colors going on in it. But it allows me to break down the scatter plot by the species of the iris. And there's a really important thing here. Let's go back up 1 second here. This is basically a flat and essentially zero regression line through the data. But when we break it down by species, and I'll scoot this over a little bit so you can see all of it, we see that they all have a strong uphill relationship, and that setosa in the red is really strong. And then we have the density plots for each variable broken down by the categories on the side. And if I click on this, again, it brings up the menu from the scatter module. And that one, by the way, goes under exploration to scatter, and has two functions, scatter plot and Pareto chart. But I'm doing this one right here. And it's a great way to get some additional insight. And so modules in general, their role is to bring extra functionality, extra things you can do with your data into Jamovi. Currently, there's about a dozen, but as Jamovi grows and develops, more people who create packages for R will learn to adapt them for Jamovi and give it even more power and even more possibilities. You may be familiar with the statistical programming language R, a free open source language that is specifically developed for working with data, and is a favorite tool of statisticians, data analysts, data scientists everywhere. One of the great things about R is how powerful it is, and that really you can do anything in it. One thing you can't do, however, is use drop-down menus. You have to type out lines of code, and that makes it intimidating for a lot of people. One of the great things about Jamovi, which is based on R, is that it helps provide a bridge between people used to menu-driven applications like SPSS and command line-driven applications like R. To show the connection between the two, I have the same analysis in both a Jamovi file, that's jmvpackage.omv, and as an R script, jmvpackage.r. Now, you're only going to be able to open that one if you have R installed on your computer, and hopefully RStudio too. But let me show you how Jamovi connects these two applications. Here's the analysis open in Jamovi. It's the iris data. And what I have here on the right is I have some descriptive statistics. And if you click on that, you get the commands. I have the menu. It looks a lot like an SPSS menu. I put the variables in there. I ask for certain statistics. I ask for certain plots. And we scroll down, and here is the basic analysis. I have density plots and box plots for each of the variables. And it's really easy to do. If I want to do the same thing in R, it's really easy to do using the Jamovi package. But to get there, you first need to enable something called syntax mode. If you come up to the top right, and click on these three dots, you'll open up a menu. And right down here under results is you have syntax mode. If you click on that, then the output here looks a little bit different. We now have a monospaced font. We have some headers here. And this right here is an R command. And what you can do is you can do an option click on that, or a two-finger click, and do syntax and do copy. And then from there, you go over to R version of this file open. I've got some header information that I put on all of my files. You need to install the JMV, which is short for Jamovi package. And once you've got it installed, you need to load it by using library. I'm going to run that command. Down at the bottom, it just tells us that Jamovi now has precedence on the ANOVA command over the stats package. And we also need to load the data sets because that's where the iris data is. So I do those two things. And now I load the data. Now, a funny thing here is the Jamovi command needs to know where the data is. And in R, you say data is equal to, and then you give the name of the data, where the name of the object in the memory. And in this case, it's called data. I know it looks redundant, but it makes it very flexible as long as you come back here and you save your data set into an object called data, which I'm going to do right here. And then you can see that it's loaded over here, 150 observations with 5 variables. I'm going to take a look at the first few lines with the head command just to make sure it's entered right. That looks exactly like it should. And then we come here to this command from Jamovi. I've already pasted it in here. It's a single sentence. This tells us that we're using the JMV package, the descriptives function. Here's the arguments that go into it, and then a few extra options. This is a single command, and when I run that command, what I get are the same tables and charts that I had in the Jamovi output. Now, let me make this a little bigger over here so you can see the tables better. This is the exact same chart that Jamovi produced. It's now a monospaced font, but it's set up exactly the same way. And over here on the right under plots, we have the same plots, but now it's showing them to us one at a time. And this is actually the last one. And you can scroll through them and see the other charts that Jamovi produced. It's exactly the same as we had in the application. And so the purpose of this package is, number one, maybe you're more comfortable with R. You can reproduce all these commands that you did in Jamovi in R. Number two, it provides a bridge. If you're familiar with SPSS and other menu-driven applications, Jamovi makes it possible to set up your analyses with menus, then copy the syntax and paste it into R. And that way you can become more accustomed and learn to use R. And in fact, because the Jamovi package really contains everything you need to get, for instance, through an introductory statistics course, you only have to learn one package. And that makes it extremely efficient and extremely user-friendly when it comes to learning a powerful language like R. Our next chapter is about wrangling data in Jamovi. And if you're not familiar with it, you may wonder what I mean when I say wrangling, because I'm not talking about this kind of wrangling out on the range. Instead, I'm talking about this kind of wrangling where you're taking data that's in a mess, it's in a jumble, and you're organizing it and you're getting it so you can analyze it. It goes by a few other names as well. Sometimes it's called data munging. Sometimes it's called data scrubbing. It can also be called data cleaning, or really it just refers to the general process of preparing your data for analysis. This is really the nitty-gritty of data. It's the part that's not so glamorous, but absolutely critical to the success of a project. It also tends to be the most time-consuming part. In fact, one of the rules of thumb of any data project is that about 80% of your time is spent preparing the data for analysis. And to help with that, we're going to talk about entering data in Jamovi, importing data, defining variables so you know what you're dealing with, computing new variables to get things ready for the form that you need, and filtering cases so you can focus on subgroups and get more detailed analyses. And as we go through all of this, you'll see the special functions Jamovi has to help you prepare working with your data and to get it started so you can discover the joy of clean data. The sample data in Jamovi is wonderful. It's a great way to learn the program, see how things go. On the other hand, you probably came here to analyze your own data. And so Theoretically, the simplest way to do this is to enter the data directly into Jamovi, because you can do that. We've got something that looks like a spreadsheet over here, and when you first open it, it's got these 3 blank variables called A, B, and C, and you can put your own stuff in there. So for instance, you can put an ID number, and in fact, it's a good idea to change the names of these so you know what they are. So I'm just going to change this one to ID, and then I'll change the next one to first name, and then I'll change the third one to age. And so we've got 3 possible variables there. I'll close this window. You want to use ID number because you need to be able to find a particular case, and you need to be able to return things to the order in which they were. So I'm going to put number 1 right there, and let's say first name, let's put Alex, and let's give an age of 34. Okay, if we were in Excel or Google Sheets, we could hit return now, and it would take us back to the first column. Jamovi doesn't do that, it goes straight down, so we need to manually, I'm going to hit the left arrow to go back. We'll do the second one, and we'll do Ava, and we'll say that she is 41. And then we'll do a third one, and we'll say it's Fikri, and we'll say that he's 18. Anyhow, you can do it this way. It's really tedious. It's a laborious process, and I really don't recommend entering the data directly into Jamovi the same way I never would recommend entering the data directly into SPSS or to R or to SAS or anything else like that. This is possible, but it's not a good way. Instead, a much better way is to enter your data in a spreadsheet. Google Sheets is good because it's online and several people can be working on the same sheet at once. And then you can import that file, which is what I'm going to show you in the next video, the much better way to get your data into Jamovi. While it's possible to enter data manually into Jamovi, it's an awkward process, and it's much better to save the data in a spreadsheet, either from Google Sheets, Excel, or some other program, and then import it directly. And fortunately, that's easy to do in Jamovi. Here I have a blank window, and what I'm going to do is I'm going to show you how to import several different spreadsheets or other formats. So first, I want you to see the files themselves. What I have are 4 files with the same data in it, but they're in different formats. This first one is an XLSX file. It's Excel, or really it's the Excel's Open XML format. And you can see we've got an ID number, recorded date and response ID. Then we have 5 questions, Q1 through 5, and then a zip code at the end. And it's a very simple data set. Now I have the same information saved as a CSV file, which stands for comma separated values. This is the really most common version of a spreadsheet that basically anything can read. And we've got the same data. It's shown a little bit differently here on my Mac when I do a quick view, but it's the same data. You can also save it as a text file where you have tabs separating the values. And actually I did this in Excel, just saved it as text. And you can see again, although it's arranged a little differently, it's the same data. And then finally, I have the same data in an SPSS.sav file. Now, it may be depending on what you have on your computer. If you click on this, it'll give you variable definitions when you do a quick view. But right now, it's not showing me anything. But here's an interesting thing. Jamovi can import most of these, but not all of them. Let me go back to Jamovi. What I do is I come over to the menu here with the 3 horizontal lines, and I hit open. And you'll see that it's able to open several different kinds of files. Of course, Jamovi files, and then CSV and text files. It's able to open SPSS files, Stata files, SAS files, and JASP, which is another program created by several of the same developers of Jamovi. Looks very similar, but operates a little differently. And so these are the options. Now, let's come up here to browse, and I'm going to go to my desktop. Desktop's right there. And what you see now is the XLSX is grayed out. I can't open a native Excel file, but that's okay because if you're in Excel, you just save it as CSV and you're good to go. So let's start with the CSV file. This is the most common kind of file that you would be importing. All I got to do is double click on this. And then it opens up in Jamovi, and there we have our data. Let me move this one over a little bit. Perfect. It's formatted, and you can see that it even changed the data types to match pretty much what's in there. Now, I'm going to show you how to do data definitions in later videos, so I'm not going to worry about that right now. But this is the CSV file. Now let me show you what it's like when we open the text file. Again, I'll come to open. And because I have this one folder open, it's my desktop, I can just hit import text. I double click on that. It takes just a moment. And here you see the data looks exactly the same. There's no difference. And then finally, we're going to do the SPSS file. And you'll see with this one, there is a small difference. I'm going to come here to import.sav. That's the SPSS data file. I click on that. And what's different here is that in SPSS, you have labels on your values. And so, for instance, you see the variables Q1 through Q5. In the other ones, they were just the numbers 1 through 5. Here they have labels on them. Although you should know that the numbers are underneath. I'm going to just double click on this. And when we open that up, you can see strongly disagree is a 1, disagree is a 2. And in fact, Jamovi can still treat these as numeric variables, the same way you would do in SPSS if you had a variable with value labels. I'm going to close that. Now there is one other thing. SPSS really didn't like having the date and the time in the same thing, so they had to get split into two. But that's a trivial thing. And so you can see that if you have the data in a spreadsheet, you got it in SPSS or SAS or some other format, it's a very quick and easy process to import that data into Jamovi. It reads the formats, it reads the labels, and then you're good to go. Your computer can analyze data without knowing what it is. If it has numbers, it'll work with numbers. If it has text, it'll do something. But for it to mean something to you as the analyst and maybe as your client, you have to know what things mean. And that means that you need to define your variables, give them their variable types, as well as put labels on them that are going to help you as you try to make sense of things. So for instance, here's a small data set. It's based on the one that I imported earlier. It begins with an ID number. That's helpful because you can go back and find particular cases. So you always want to start with that. Then I have 3 questions, Q1, Q2, Q3, that are on 1 to 5 rating scales. And then I have a question here. I've called it subscribed at the end, and it's yes and no, or Y and N. Now, what we need to do is say what kind of types each of these variables are, as well as give them labels as necessary. Now, ID, we don't really need to worry about this one, but by default, if a Jamovi sees 1 through however many numbers, it's going to assume that it is a continuous scale. Now, we want to change the type. You can do that either by double clicking on the name of the variable here, or by going up to data and then clicking setup. Either one will work. And so the very first one is ID. Now, technically, ID numbers are not continuous or quantitative. They're nominal, where it's 1 per person. So I'm going to put nominal, but I'm going to say integer. That's fine. And we'll leave it like that. And you see now that its little icon here has switched from the ruler to the 3 circles, which indicate different categories or buckets. That change, by the way, from ID from continuous to nominal, it doesn't really make a difference. I'm going to go to the next variable, which is Q1. And this is where I actually want to give it a real name. And I might say something like website. So do they like your website? And now that shows up here. Now this isn't the label. I just changed the name of the variable. I could give it a more thorough description. Does the user like the company's website? Now that label there is just for our own use. It doesn't really show up anywhere. But what I'm going to do here is I'm going to change the variable type, and I'm going to change the names of the levels. Now, it turns out that when you have a small number of categories, or 1, 2, 3, 4, 5 is a small number, Jamovi assumes that it's a categorical or nominal variable. The thing is, it doesn't really make a difference. If you're going to be averaging, or if you're going to be calculating statistics, it'll do it on these variables, even though they're defined as nominal. You can change it to continuous or ordinal, and that's going to affect the kinds of graphs that you can make, and is going to affect the ways that you can split the data. So it's not critical if all you're going to do is average, but if you want to do other things with it, it helps to define them. Now, a 1 to 5 rating scale, there's a debate about what level of measurement it is. Technically, it's ordinal because higher numbers indicate more agreement or a higher evaluation of something. On the other hand, in every field I've ever seen, people actually take a 1 to 5 rating scale and treat it as though it were continuous or quantitative so they can average it. And so I'm actually going to come here and I'm going to define this one as continuous. Now you'll see here that the levels went away because now it's treating these as, like time, 1 seconds to 5 seconds doesn't have labels. And so that's fine. And I know what it means. So I'm going to go ahead to the next one. And I'm going to put here like price of your service. And this one, I'll put it as ordinal. Now you see that the levels here stayed, and that's important. And the last one here, I'll just put like product. And I'm going to leave this one as nominal, but now I'm going to change these levels. So I'm actually going to change these labels. So for instance, I click right here at 1, and that's usually strongly disagree. And then the 2 is disagree. The 3 might be neither. 4 would be agree. And 5 might be strongly agree. A lot of people call this a Likert scale. It's actually a response scale. Likert scales have more to do with how you choose the questions as opposed to the format in which you respond to them. But call it a Likert scale if you want. It's a 1 to 5 rating scale. And now you can see that these labels all show up down here. That's really a convenient thing. And remember, the numbers are still underneath there, so you can still do numerical operations on these variables. The last one I want to show you is this text variable at the end. You see it says nominal text because I actually typed in the letters Y and N. And you can do the same thing with these. I can click on the Y and I can put subscribed. And I can maybe put they're not subscribed, but they came to your website, so we'll call them a visitor. And so now you have new names for the variables. I changed the names. I changed the level of measurement or the type of the variable for some of them. Say, for instance, from continuous or quantitative to ordinal to nominal or categorical. And then I changed labels. And so this is a very important step in terms of preparing the data in Jamovi because it's going to make it much easier for you to interpret the analyses and then in turn to make sense of it, especially when you're collaborating with a colleague or potentially working for a client. One of the most common transformations on data is averaging several variables. That way you can get, for instance, a scale score. It's also a great way of helping balance out the error variance of different scores and really get you more generalizable information. This is easy to do in Jamovi. What I'm going to do is I'm going to take this data set that has ID and it has these 3 rating scale questions. And they're all on a 1 to 5 scale, and they ask people how much they liked different elements of, for instance, your website. And I'm going to click on each of these first. We'll go to like website, and we have a little bit of descriptive text, and it's a continuous or quantitative variable that's just on a 1 to 5. If we go to like price, you see it's ordinal, and even though it's ordinal, you get to specify levels. Now it just has the 1 to 5. That's easy to do. And then like product, you see here in the data, it has text. It says neither, strongly disagree, and so on. And then it's coded as nominal. On the other hand, it's important to say that it's an integer variable, even if it's nominal. And then over here, we have levels where we have the 1, 2, 3, 4, 5, and we've put labels on each of those levels. So 1 is strongly disagree, 2 is disagree, and so on. The reason this is important is because the numbers still are there underneath those labels. And that's what makes it possible for us to average them. So I'm going to close this for just a moment, and we're going to create a new variable. I'm going to double click right here. And I can either enter a new data variable, a new computed variable, or a new transformed variable. We're going to do the middle one right here, a new computed variable. And it's going to ask for the name of that new variable. I'm simply going to call it the mean. And we can give it a description if we want. I'm going to put down here the average of 3 rating scale variables. The easiest way to do this is to come to the function window. And if you're used to SPSS or to Excel, you know you got a lot of different choices. There's a much smaller range in Jamovi, but they're basically the ones that you need. I'm going to scroll down a little bit and get to mean. And I'm going to double click on that to put it in the box. And then I need to tell it what variables I want to include. I'm going to come over here to the variable list and simply double click on the first one. And when I double click on it, it puts it up here, and you'll see that it puts it in backticks. Those are sort of back-leaning apostrophes. That's because there's a space or a non-text character in here. If you had an underscore or a dash, it might do the same thing. It's actually a nice reason to not have spaces or other things in your variable names, because then you don't have to do the backticks. But Jamovi is going to do that for us automatically. Now, when you have a range of variables that are all next to each other, in SPSS, you can give the name of the first one and then write TO, capital 2, and the last one. In Jamovi, you need to specify each of them separately. So I'm going to put a comma, and then I'll click the second one, and a comma, and I'll click the third one. And now I've got that, and I can close this. And you can see it automatically fills in with the mean. Even though there are 3 different levels of measurement, it knows that they'll have numerical information. Now, I said it was important that this one right here was specified as integer. Let me double click on that again. And then you'll see if I come down here and I say it's not integer, but it's text, then you see the mean disappears, even though those levels still remain. But if I come back and tell it again, no, it's integer, then the mean reappears. It's able to treat it as numeric information. And so that's how you can average several variables in Jamovi, which gets you a long way towards getting more reliable scores, averaging out some of the variance, and getting the scale scores that you may need for your further analyses. Sometimes your data comes to you on scales that don't have any inherent meaning or may not be familiar. A 1 to 5 or 1 to 7 agreement scale, well, it's common, doesn't have inherent meaning. And if you're comparing income information from Nepal to Turkey to Mexico, you're going to be dealing with different currencies, and you're going to need a way of comparing relative standing. The easiest way to do that is with z-scores or standardized scores. Now, if you've had statistics, you know that that simply takes the score, subtract the mean of the variable, and divide by the standard deviation. And a lot of people show you how you can do that manually, and you can set that up in Jamovi that way, but there's a much easier way to do that. Let's do this one. We're going to come here and double click on this empty variable here, and we're going to choose New Computed Variable. And what I'm going to do is I'm going to change this to say z-score, and then I'm going to use the function window and scroll down to the statistical functions to the last one on that particular list. It's z. I just double click on that. It brings up the function, and then I need to tell it what I want the z-score of. In this case, I want the mean. That's the mean score of those 3 rating scale questions. I double click on that, and I can close the window. And there it is. That's all I need to do. A negative z-score indicates that somebody is below the mean. A positive z-score says they're above the mean. And the numbers themselves are units of standard deviations. So this very first score that's highlighted is 0.4 standard deviations below the mean. Quick and easy, and Jamovi makes it a cinch, and that helps you get on the way to taking your variables that are in different scales or arbitrary ones and putting them into something that may be more meaningful and is certainly more comparable from one variable to another. When you're getting your data ready for analysis, sometimes you need to do the same transformation to many different scores, like doing reverse coding or logarithmic transformations. Or maybe you need to take variables and convert them into ordinal categories. I want to show you an example of how to use Jamovi's transform function to take z-scores and identify whether they are extreme or not using the plus or minus 2 standard deviations criterion. What I'm going to do is I'm going to come over here and click on this blank space, and then I get to choose a new transformed variable. Now, what I'm going to show you can be done with a computed variable, but the advantage of doing it with a transformed variable is it saves that transformation function, and then you can apply it to multiple variables at the same time if you want. The first thing we need to do is we need to define the actual function that we're going to use, the transformation function. And so I'm going to come right here to transform. I'm going to click on that, and right now I don't have any transforms. I'm going to come down here to create new transform, and that brings up another dialog from the bottom. And now I'm going to label the transformation. And again, this is something that can be applied to multiple variables. And so it's not the name of a variable, but it's the name of what you're going to do to variables. And I'm going to call it extreme. And I'm going to say, is score more than 2 standard deviations from mean? And I'm going to be using the z-score so I don't have to compute everything else. And then what you have here is a variable suffix. And the idea is that if you have many different variables like Q1, Q2, Q3 for question 1, 2, 3, and you're doing a logarithmic transformation on all of them, it can create a new variable that includes, for instance, Q1 underscore log or log and then in parentheses Q1. There are a lot of different ways to do it. I'm just going to put this right here and say extreme. And then I'm going to do the recode condition. Now, right now, it's asking me just to replace it with something else. I have to do add recode condition. And source means the variable that you're starting with. And again, you can leave that there because you're going to choose that variable in the next dialog box. I'm simply going to say, if it's greater than 2, then I'm going to say assign the text yes. And you have to put text in single quotes so it knows, otherwise it's going to try to read it as a variable name. Then I'm going to add another recode condition and say if it is less than -2. And then that is also extreme, so I'll say yes. And then else says otherwise, just do this. Otherwise it's no. So that's simple. So I'm going to close that, and now I've defined that transform function, and you can see that it's available now. There's extreme right there. And I'm going to use extreme, but it wants to know what variable it is I want to transform. That's why there's the question mark there. So I'm going to come right here, and I'm going to choose z-score. And once I do that, you see it fills in immediately where we have the nose, and down here we have a z-score of 2.097. That's greater than 2, so it says yes, that's extreme. And this is a function that I could apply to other variables if they're on the same scale. And so it makes it easy to prepare a lot of variables, sometimes using rather complex functions, but rather quickly in a way that's easy to set up and easy to understand what's happening. One of the important steps in analysis is the ability to drill down, to focus on specific cases in your data set. Jamovi allows you to do that by filtering cases. To do this, I'm opening this data set that I've called filtering cases, and I'm showing you a little bit of descriptive statistics here. The number of cases, 173, and the minimum and maximum for 2 of the calculated variables at the end of the data set. To get to filters, come here to data, and click on the filter. It looks like you're pouring filter in a kitchen. And when you click on that, you get the opportunity to enter your text for a filter. You can click in here, and you can choose various functions, and you can choose existing variables, and you can simply click on them. So I can go, for instance, ID, and then less than 10. And that will give me the first 9 cases, those that have ID numbers less than 10. And I have a variable over here called ID. So I'm going to hit return for that. And now what you see is I have a new column here called filter 1. You can't change the name of the filters. They're just 1, 2, and so on. And I have a green check mark for all of the cases that are selected, and you see them here, and a red X for all of the cases that are not selected, and their rows are grayed out. And now you can see that I have only 9 cases, and we have different statistics because they're calculated only for those particular 9 cases. By the way, if you want to close this, just hit the up button like that. And there's our 9 cases from our first filter. But you probably want to do more than that. And so Jamovi allows you to use more than one filter in combination or trading off with another one. And it allows you to do more sophisticated filter commands. Let me come back to filters here. And I'm going to add a new filter. I'm simply going to press the plus. By the way, what the I here does is it shows or hides the filter column that's on the left. You see here it says filter 1. If I hide that, then you just don't see it anymore, even though the filter is still operative. I'm going to do a new filter, and this time I'm going to paste something in. And what I have here is a filter that draws on this calculated column. So I'm going to hit filter, and I'm selecting all cases with a mean greater than 4. And if I double click on this, you'll see that the mean comes from the average of these 3 variables, 1, 2, and 3, even though this one has text, but note that if I click on it, you can see that there are numbers underneath it. And I'm going to show you how that works in a later filter. But now I have this second filter, and you can see I only have one case that's selected because I'm using both of my filters at once. If I only want one filter, I'm going to come back here to filter 1, and I'm going to make it inactive by turning it off. And now I have more cases that are showing. Coincidentally, it's still only 9 cases that have values of more than 4 on the mean. I'm going to make another filter. First, I'll turn this one off. I'm going to make a third filter here. And this time I'm going to paste it in. And what I'm going to use is the z-score variable. That's 1 over here. Now, the thing you need to know about z-score is because it's got this dash in it, I have to surround the name of the variable with backticks. Those are where the tilde key is to the left of the 1 on your keyboard. Now, if you select this by going to f of x and you simply click on it, it will automatically put in the backticks. And this time, I'm putting in something less than 2 and more than 2, but I'm getting a problem, and that is it doesn't want to do it because it says I have a v or column function. That's because z-score, let's go back to this, z-score depends on the mean of the variable that we're looking at, which is mean, and the standard deviation, which means it has to calculate that for all of the cases that are in that column. You can't do a filter on that. You get sort of an infinite regress. So I'm going to come back to here, and I'm going to turn that filter off, but I'm going to show you the way that you can do that. Now, one choice is to simply copy the values in the z-score variable, paste them into a new one, and now they're no longer a formula, they're just text, and you can operate them like any other variable. But that really compromises the functionality of Jamovi. You lose the ability to easily replicate the functions because that's not a formula-based approach. A better way to do it, even though it's slightly more complicated, is to include the z-score function in the filter itself. So let me come back here and click on this new filter. So you see I now have a filter 4 right here. I'm going to paste in a filter. And now I actually have the z formula in the filter. And when I hit return, now we don't see the z-score for this one anymore. It had a value of 4.33. That's going to be a high z-score. But you can see that all of these others are within a particular value. Now this is nice if you want to choose the cases that are between 2 values, but often when you're using z-scores, you want to look at the extreme cases to identify outliers. And the intuitive thing would be to simply flip around these relational operators, the less than signs, to make them greater than signs. But let me show you what happens when you do that. First, I'll turn this off. I'll create a new filter. So it's filter number 5, and I'm going to paste it in. And you see, this one's the same as above, except I flipped around the less than and replaced them with greater than signs. Well, I'm going to get a problem with that one. And what it is it's excluded every single case because of the way it's parsing the logic of this one. This doesn't work. Instead, what you need to do is you need to do 2 separate statements joined by an or. So I'm going to turn that one off, open it up, and paste in this other filter. And now you see that I say z for the mean score is either less than -2 and then or z mean is greater than 2. Please note, in a lot of languages, things like and or need to be in capitals. In Jamovi, they need to be lowercase. Also, if you're writing in a language like R, you can use the pipe, the vertical line character, to signify or. That doesn't work here. You need to type lowercase or. And when I run that one, now you can see that it's selecting cases that are unusually high and also some that are unusually low. So we can join the 2 in a single statement to filter out and get the extreme cases. Now I want to show you one more example of how filters work. First, I'm going to make this one inactive so we have all the cases again. And I'm going to press plus, and then I'm going to paste in my 7th filter. And this one uses the variable like product. That's this one right here. Again, because I have a space or a non-standard character in the title, I have to put the name of the variable in backticks. By the way, that's a good enough reason to never have spaces in your variable names. That way you don't have to do something like that. And I'm going to select cases that are either 4s or 5s. Now, in this case, I'm using 4 because I know that's agree. In fact, let me just run this, and I'm going to click on this again. You'll see here that 4 is agree and strongly agree is 5. And you can use either the value or the label. But if you use the label, you need to put it into quotes, not backticks, because backticks are only for the names of variables, but in quotes. Also, if you're not familiar with programming, you know that you don't use equals, because that's usually what's called an assignment operator, say this variable gets this value. You have to use the two equal signs together, and that means is equivalent to. So like product is equivalent to 4, or like product is equivalent to strongly agree. That gets me the 4s and the 5s, the agrees and the strongly agrees. And so that's an exploration of how filters operate many different ways in Jamovi. They allow you to focus on particular cases, to find the things that are most interesting in your particular data set, and drill down to focus on those, give them the attention they deserve, and hopefully get some new insights out of your data. Our next topic in Jamovi is exploring data. And the reason we need to do that is because raw data is just completely overwhelming, even when it's set up in nice rows. Instead, you need to get a map. You need to know what you're dealing with and get the lay of the land so you can tell a coherent story. Now, in Jamovi, we have several options for exploring data. First off is regular descriptive statistics, things like the mean and the median and the standard deviation. But even more useful than that are data visualizations like histograms or density plots, box plots or violin plots, or a dot plot, in this case, combined with a violin plot. And finally, standard bar plots, one of the most useful methods for visualizing data. We'll also talk about how you can export these graphs, these tables, to docs like Google Docs and Microsoft Word, and to presentations so you can share your insights and get your message across. Perhaps the quickest way to get some insight into your data is to do basic descriptive statistics, like frequencies and means and standard deviations. Fortunately, that's really easy to do in Jamovi. Now, the data set that I have open here is the bugs data set, where we have a number of people, and they are rating how much they would like to get rid of bugs that are either high or low disgusting or high or low frightening. And we have the people's gender, region, and education. And all we need to do is come over here to Exploration and click Descriptives. Now, I've installed the scatter module, so these two menus show up here. If you don't have those, that's not a problem. Just hit Descriptives. And then we get to pick the variables we want, and Jamovi will either give us means and so on or frequencies. Now, I find it useful to start with the predictor variables, the ones that you're going to use to predict the outcomes. And in this case, that's going to be these three categorical demographic things: gender, region, and education. So I'm going to put those over here into variables. And what we're going to get is a table that really only tells us how many cases there are. There's 91 or 92, and we're missing 1 or 2 on each of them. I don't need these other variables because these have to do with quantitative or continuous variables. So I'm just going to remove those for right now. On the other hand, because I have nominal or categorical variables, it would be nice to get frequency tables. So I'm going to click this selection right here, and then it's going to automatically expand, and it's going to give me the count, the number of people in each category, along with the percentage of the total data and the cumulative percent. And so, for instance, we can see that we've got about 2/3 women and 1/3 men, and that we've got a lot of people from North America and almost 10% from Europe, but other groups are pretty small. And level of education, we have a spike at less, and we have 15 people or 16.5% at high, which I assume means high school. Anyhow, this is the first step. Get some basic demographics or the things that you're going to use as predictors. Now, I also want to look at the outcome variables, which are scaled. They're measured on a 1 to 10 or 0 to 10 scale. And I'm going to do the descriptives command over again. I'm going to hit descriptives, and then it shows up as blank. And what I'm going to do is I'm going to take these 4 outcomes and put those in the variables over here. Now this time, because these are scaled or quantitative outcomes, it's going to give me mean, median, and so on. On the other hand, there's a few that I should add to that. Most importantly is the standard deviation. That's sort of a bare minimum for how spread out things are. It's also nice to have the quartiles. Now, if you want to, you can add the standard error, the mean, or the variance, and you can get skewness and kurtosis, each with its standard error. But this, what I have right here, is usually plenty. By the way, you may notice that this table strongly resembles the command that you use in SPSS to get basic descriptive statistics. That's on purpose. Jamovi is modeled to be friendly to people who are migrating from SPSS, and then it brings in the power of R, but it's designed to be accessible. And so now we have some descriptive statistics on the categorical demographic variables. We have some descriptive statistics on the quantitative or continuous outcomes. There is one other thing that we can do here that's worth mentioning, and that is we may want to look at some of these variables here, the outcome variables, and break them down by one of our other categories. The only one that's going to work really well here is male or female. The general rule of thumb with quantitative variables is you want to have at least 10% of your sample in the smallest group. So we would probably have to combine people to be sort of North America or other, but I don't know that that would make a lot of sense. But what I can do is I can get the statistics for these 4 outcome variables, how much people want to get rid of these various bugs in terms of how disgusting or frightening they are. And I can break that down by gender. To do that, I come back up to exploration and go to descriptives. I pick the 4 outcome variables, which again stand for like low disgusting, low frightening, low disgusting, high frightening, and so on. And then I get our nominal or categorical variable gender, which is text in this case, because they actually wrote out male or female. And then I put them down here, and then I'm going to come and make a few changes to the table that I'm going to get. Mostly, I'm going to remove some of these statistics because when you start breaking it down by other categories, it gets really busy. And so I'm just going to get the N, the mean, and the standard deviation. And that's probably going to be sufficient for what I'm doing right now. And here you can see how it broke it down into those categories. I can click out here. And so that is a quick run through of the descriptive statistics that you can get quickly and easily in Jamovi. Again, a very good first look at your data and a way to get started on understanding what you have to help you shape and then interpret your analyses. The way Jamovi is set up, when you first go to explore your data, it offers you descriptive statistics or a numerical insight into your data. On the other hand, I actually prefer to begin with pictures, graphics, visualizations. Do those first and then get numbers to provide precision that's in addition to what you get from the graphics. So in this one, I'm going to show you the first of several different visualizations that we get from Jamovi. The first one is histograms. Now the data set that I have open is the iris data. This is one of the example data sets. I'm going to come over here to exploration, click on that and go to descriptives. Now, by default, it's going to try to do statistics. I actually don't want statistics, so I'm going to preempt that and just remove this information right now. So it's not going to produce a table. So the table's gone. What I am going to do, however, is I'm going to select these 4 quantitative variables. These are measurements of the petals and sepals from 3 species of irises. I'm going to put those in variables. Now, right now it's doing nothing because I canceled all of the statistics, but I need to come to this menu, which is plots. And all I'm going to do is select the first one, which is histogram. Remember, a histogram is a chart like a bell curve that shows you how common each score is in a distribution. The width of each bar, or the bin width, is arbitrary. In a lot of other programs, you can adjust that manually if you want. You can't do that in Jamovi, but truthfully, right now, it just makes your life a little simpler. What we have here is a pretty strong unimodal distribution for sepal length. We have kind of normal with a big spike in sepal width. We have a strong bimodal distribution for petal length, although it might be 2 separate normal distributions, maybe. And then for petal width, again, strong bimodal with this really skewed distribution here on the far left. So this lets us know, by the way, when you get a bimodal distribution, that generally tells you that you have more than one distribution happening there that got combined. And that makes sense because in this data set, we have 3 different species of irises. And with that, it makes sense to split this up and look at each of the species separately. So I'm going to do this command again. I'm going to come back up to exploration, to descriptives, and then I'm going to select the 4 variables again, put those into width, but this time I'm going to add this one. I'm going to put species under split by. I'm going to cancel out these statistics again. Those aren't what I'm looking for right now. But I'm going to get histograms. Now what we have are separate stacked histograms for each of the 3 species. Now, it does a really nice thing in that it puts all of them on the same scale. So for instance, here on sepal length, all 3 of these go from 4 centimeters up to 8 centimeters. I'm going to click over here to close the menu. And it puts the 3 different species or 3 different groups in different colors. So it's really easy to tell them apart. And you can see Setosa is the lowest, versicolor is kind of middle-ish, and Virginica is a little higher. For sepal width, you can see that we've got some big differences there, where Setosa is now the highest, and versicolor and Virginica are pretty similar to each other, although we have an outlier on Setosa. And then for petal length, we have an enormous difference. Setosa is way down there at the end, and the other 2 are pretty close to each other. And then finally for petal width, you can see the skewed distribution that's really close to 0 for the Setosa irises, whereas versicolor is a little bit medium and Virginica is at the highest. And so this is a great first step for getting a visual exploration of your data. First, by combining all the groups in one, and when you get an indication that maybe there's something going on there, then splitting it up to see if you can drill down and get a little more explanation for some peculiar results like bimodal distributions or skewness. And that's what we get from these separate, stacked, small multiple histograms, which are very easy to do in Jamovi and really a great way to start breaking down your data. When you're looking at the distribution of a quantitative or continuous variable, a histogram is usually the first choice, and that's what I have right here. And in the last video, I made histograms. Here I have it for the entire variable with all 3 groups combined, and then down below, I have the 3 groups separated out. And this is a nice way to do it. However, another alternative that truthfully I prefer is to smooth out the choppiness of this a little bit with something called a density plot. And to do that, let's simply click on the existing analysis. One of the nice things about Jamovi is that when you click on an analysis, it brings up the menu that produced it. And so here we have descriptives. I've got the 4 quantitative or continuous variables here. I have all the statistics turned off because I didn't want a table there. And I've got histogram right down here. Now, the reason histogram and density are both listed below the histogram's title is because it can layer them. Now, I'm going to do that to show the relationship, but then I'm going to separate it. So I'm just going to click density right here, and this will be laid on top of the existing histograms. And so what you can see over here is our original histogram with this little blobby kind of shape over it, which is a lot like a smoothed out histogram. And you can see a similar shape on all of these. Now, it doesn't follow it really exactly because it's averaging across. But you see this same general trend, strong bimodal distributions, and right here as well. Now, to make it a little clearer, I'm actually going to turn off the histogram. That'll leave us with just the density plot. You can see the density plots without the histograms, and the scale adjusts, and so it makes the pattern a little more pronounced. But that's our first indication. We get these blobs, and you can see sort of unimodal. Unimodal is really kind of triangular, but kind of close to normal. Strong bimodal, strong bimodal. And then we come down to this second set, and I'm going to do those as well, simply by clicking on the analysis. And this is where you have the 4 variables, but they're split by species. And again, all I need to do here is click density, and that'll lay the density charts on top of the existing histograms, and then I'll turn off the histograms. Again, and I actually prefer to do density instead of histograms because it smooths out and makes the pattern a little easier to see. But you can see it does the same thing where it colors them, it stacks them by the 3 different groups. And I'm going to turn off histogram so we can see what it looks like without that. And this is where the pattern really kind of comes into focus. We have the three different groups, and you can see the mounds or the piles of the data in ways that make it clear that the distributions are basically unimodal here, but they're in different locations. A little bit difference in skewness. You come down to petal length and the differences become very clear. And I think that by using the smoothness of the density plot, it becomes a little easier to see the overall pattern and not get distracted by the jaggedness of the histograms. And so density plots are another really helpful way to look at a quantitative or continuous variable, either for all data at once or breaking it down by subgroups. The more you work with data, the more you learn that outliers can be a really serious problem. They can throw off your analyses and your conclusions dramatically. And so you want to pay special attention to the presence of outliers in your data. And probably the easiest way to do this is not with a histogram or with a density plot, but with a box plot. So in this example, which uses the iris data and starts up where we left off with the density plots, I'm going to do box plots and show how they relate to the density plots and the extra insight we can get from them in terms of identifying outliers. Now to do this, I'm just going to click on my existing density plot analysis. And then when that opens up, I'm going to come down here to plots and I'm going to click box plot. Now you notice this is in a separate column. And what this means is it's going to produce a separate chart. So the density plots aren't going to go away. This will be in addition, but I'll then remove the density plots. So here come the box plots. Scroll over, we'll see that the box plot is directly underneath the density charts. And in the first one, there are no outliers. This one, we get a few outliers on each end. That's not surprising because if you remember your statistical terminology, this is basically a leptokurtic distribution. It tends to have a lot of outliers. With petal length, we don't have outliers, but that's because of the bimodal nature. The middle part of the box plot is spread out so much. And then the same thing is true down here at the bottom. Again, when it's spread out like that, lets you know something really unusual is going on with your data. I'm going to turn off the density charts in this analysis. And so we'll have just the box plots at this point. Now, you can do the same thing with grouped analyses where you split it by something. So I'm going to close this analysis for a moment and come down here where we had our stacked density plots showing the data for the three different species. If I click on that, I can do the same thing that I did. I can get a box plot. I'll click box plot. And it's going to show up directly beneath each chart. Now, this time we lose the pretty coloring, but it's easy to see what's going on. We have an outlier for Virginica. We have two outliers each for Setosa and Virginica. You know, these are pretty symmetrical. They don't look bad. I'm going to come here and turn off the density plots. And so we can have just the box plots. And then we come down to petal width and we can see we got something really serious going on here because this one is so squished. Its distribution is so narrow and it's so far away from the others. That lets us know that we have something really important going on. And then the petal length, the same idea. And so box plots are a good way of identifying outliers. We don't have any massive outliers in this data set, which tells us that we're in pretty good shape. But what we do have are strongly differing distributions. On the other hand, if you're doing something like the analysis of variance, that's kind of what you're looking for. And this just confirms our insight that the three species of iris differ significantly in some of their measurements. The box plots are a good way to check that. And again, a good way to check for the potential influence of outliers in the data. Jamovi includes one really kind of unusual, kind of funny looking graph. It's called a violin plot. And what it is, and it's sort of the box plot version of the density plot. And it just kind of spreads out and you'll see why it's called a violin. I'm starting with the iris data set from the example data, and I'm using the box plots that I created in the last video. I'm simply going to click here where I have the four variables and I'm not splitting them by anything. And I'm going to come here over to plots. And again, the reason violin's right here is because Jamovi is able to stack all three of these on top of each other. You don't want to do that because it gets really busy looking. But I'm going to show you the relationship between the box plot and the violin plot by simply adding it right here. When I do that, you get a shape that looks a little bit like a Rorschach ink blot. that actually corresponds to what's happening in the box plot. Here, for instance, you can see that we've got a lot of data here in the middle, and that's where the violin plot goes out the most. We get a funny little manta ray shaped one here because of our strongly leptokurtic distribution. And down here, you can see why it's called a violin plot, because we get it comes out, it goes back in, it comes out because of the bimodal distributions that we have on these two variables. Now, I'm actually going to remove the box plot so you can see just the violin plot on its own. And what we're left with is really just a little bit of squiggles. It feels like, again, a projective test. It's a little hard for me to read, but it's an interesting version. Again, it's like a density plot, but oriented in the same direction as the box plot. You can, of course, do the same thing with the subgroup analyses that we have down here, where we broke down the measurements by species. I'm going to click on that to open up this menu, and there you can see we have species there. I'm going to click violin, and then I'm actually going to also unclick box plot right now. And what we have feels like a little set of drawing of ghosts or something, but you can see the distributions for the 3 different species, and it really feels like we're looking at a chart of animal shapes. There's a nice little bat down here, but you can see this shows that it's a strongly compressed range because, again, the outcome variable petal length goes vertically here. And then petal width, you can see again, we have a very unusual distribution for the setosas. Well, things are almost kind of sort of normal for the versicolor and the virginica. And so the violin plot, not a very common choice, but potentially an interesting one, and it might be able to give you some extra insight into your data. Box plots and violin plots are a nice way of summarizing the distribution of a quantitative or continuous variable, but maybe you actually want to see the data directly. And dot plots are a way that allow you to do that. I'm beginning with the violin plots that I made using the iris data from the example set. And then I'm going to click on the analysis to open up the commands. And I'm going to come back down here to plots. I'm going to move this up. And what I'm going to do is simply add data. Now, a lot of times you don't want to have things stacked where you have more than one kind of plot on top of another. The violin and the data, it works kind of well because the violin's an empty shape, and here you have the data in there. Now, what this is every data point in the data set, there's 150 in this particular case, and they go from the lowest score up to the highest score. And you can see how they approximately match the density of the violin plot. Now, this is called a jittered chart, because really every dot should be exactly on a line here in the middle. But that makes it hard to tell how many there are in a particular place because they might lay on top of one another. And so jittering is randomly spreading them out a little bit to the left or to the right. So they're not usually on top of each other, and it's a little easier to see the density of the distribution. I'll show you some others here. On the other hand, you have another choice. Instead of just jittering, if you're a nice and orderly person, you can also select stacked. And what stack does, instead of distributing them out randomly, it puts them exactly where they need to go and arranges them out in mirror image patterns as you go up the chart. And so again, this will appeal to those of you who are very fastidious, but now you can see a little clearer the distribution of points at each value. And you can see really how the violin plot mimics that. I'm actually going to leave the violin plot on. Normally I would remove it because the two go together nicely. They don't compete. And then I'm going to come down here to where we have our same violin plots, but broken down by the species. I'm going to click on that to bring up that analysis. And then I'll click on data and I'll leave it at stacked. Now what's interesting is I said stacked, but that appears to be jittered. So I'm going to see if I can get its attention by switching back and forth from jittered to stacked to see if it changes anything. That was just a small glitch, but by going back and forth, we straightened it out. And now you can see how the data are arranged within each of the violin plots. And the height and the width of each of the violin plots now makes a little more sense. And so a dot plot of this kind, either jittered or probably stacked is a little easier to read, lets you see what's going into the box plots or into the violin plots, and lets you see the individual data points that are going to drive your analysis. The last kind of chart I want to show you in exploration is actually the simplest and truthfully is often the most useful. It's just a bar chart. And all that does is it shows you the number of cases in a category. Now, for this example, I'm going to go back to the bugs data. And this time I'm only going to be focusing on the gender, region, and education variables. Those are the categorical or nominal ones. And I have frequencies for each of those over here. First, I have the frequencies for each variable without breaking them down. So I have the number of female and male respondents, the frequencies for region, where most of the people are from North America, and the frequencies for education. I'm going to click on this analysis to bring up the menu. And here you can see how those three got put over here. I turned off all the statistics. I turned on frequency table. That's how I got that. And now I'm going to do just one little click here. I'm going to come and click bar chart. And you'll see that Jamovi knows to do that automatically when you have nominal, that is categorical, or ordinal variables. And that's what I have here. So I can click that. And then it's going to produce the bar charts directly below the tables that I already have. You can see that it says plot now. And then it's easy to see we have about twice as many women as men. Then we have an awful lot of people from North America in this particular sample, and that the education is spread around in kind of a peculiar way. But this is a good way of looking at a categorical variable. It's so much easier to get them from a bars, and especially from bars because all they require is a relative linear judgment as opposed to a pie chart. Jamovi doesn't even do pie charts. That's because they're often harder to read. So I'm going to close that one. And then I'm going to come down to where I have the tables here. This is where I've broken it down by gender. So let me click on this one. And you can see I'm getting a descriptive analysis of education split by gender. And that's why we have education down the side here. And we have gender across the top. And I've turned off all the statistics. I have the frequency table on. And now I do bar plot. And what this is going to do is give a paired bar plot or grouped bar plot where it puts them together for each group. I'm going to close this window here and then move this over a little bit so you can see the whole thing. And now what we have are our 6 different levels of education from advanced to some. Again, these are in alphabetical order. There's a natural order to these things where more education should be further to the right and less education should be further to the left. But we also have our gender indicated by the colors. So for instance, we have the reddish orange for female and sort of a teal color for male. And from this, it's easy to see that we have a lot more women in each category with the exception of partial over here where it's just a couple of people in each and college. But the other ones have about the 2-to-1 ratio that we have overall. And so a bar chart and a grouped bar chart is really a simple way of getting insight from a categorical or nominal variable. Again, often the easiest, the simplest kind of chart, and really can be the most informative when you're trying to get some quick insights from your data. So once you've conducted your analyses and you've created all these amazing visualizations, you want to be able to share them with other people so they can get the same insight out of the data that you got in the process. Fortunately, Jamovi makes that easy to do. And what I'm going to do here is in the file Exploring Tables and Plots is I have a table that I created showing the measurements for the iris data set. And then beneath it, I've created graphs broken down by species for each of the measurements. And I want to show you how to put these into Microsoft Word, PowerPoint, Excel, and then Google Docs, Slides, and Sheets. Let's start with the table at the top. Now, what you need to do is you come over and you do an option click or control click or a 2-finger click, and you get the table and you can say copy. Now, if you want to copy it, see it says it's copied it. And now I'm going to go to Word. So I'll come down here, I have Word open, and I've got a Word document, and I can come right down here and I'm going to paste it. So I'll go to Edit and then Paste. And what you find is it actually looks really beautiful. It's nice. It is a little tiny bit funky sometimes. It has some columns in here that are invisible. There's a little in between column right there. But it looks really good. Now, if we want to put that into PowerPoint, I'll come down here and open up PowerPoint. And I'll come to this page. And I'll come over here and I'll just press paste. And now it looks kind of weird because what it's actually pasting is an HTML table. And you see, it doesn't even give us the last row of data. And then of course, PowerPoint wants to do pretty things with it. I'm going to close that. But this is not a good table. It worked better in Word. Let me go back to Word and we'll take a look at it again. It worked. We got all the lines of data. It did not work so well when we went into PowerPoint. What's usually the best when you have a table is actually to put it into a spreadsheet. So I'm going to go to Excel here, and I'm just going to do the paste command. And now you can actually see that it has these empty columns in between each of the measurements. So you'll need to move things around a little bit. You'll need to put the pedal width, take it from here and put it over here and so on. But it also allows you to easily rearrange, resize things, make them the way exactly you want. And so copying a table, sticking it into a spreadsheet like Excel is often the best way to work with tabular output. There is one other option I just want to mention. Let me come back to Jamovi. And you may have noticed that you had the option to save. Now, this gives you two different options. You can save it as a PDF, and I'll just call this table PDF. And once that's saved, you see it says it's exported. I'm going to come down to my downloads folder and I will simply click on that. It's a very pretty PDF. Looks great. The other option is to save it not as a PDF, but as an HTML file. So I'll call that table, and it's going to put .htm on it. I'm going to save that. And then I'm going to come down and open up that file. It'll open up in a web browser. And there it is. It looks exactly like what we had in Jamovi. So that's one way of doing all of that. Now let me show you how this works with Google Docs and Slides and Sheets. It works a little differently. I'm going to take this table, which I've copied. I'll just copy it again. Copy. And I'm going to go to Google Docs. I'm going to come right here to this. I've got a doc open right here. I'm going to come down a little bit, and I'm going to hit paste. And unfortunately, it doesn't always work well. On this computer, it's not letting me select anything. There seems to be some kind of glitch, and you can see that the cursor has stopped blinking and it won't let me scroll. So what I'm actually going to do is I'm going to close that page and then I'm going to open it back up. And when I do that, it's there and I can scroll, and you can work with it. I don't know why it does that. It's a little frustrating. And obviously things need to be resized and rearranged a little bit, but there it is. It's in Google Docs. If I want to put it in a presentation, in Google Slide presentation, I can click on this page and I can press paste right there. Now, it's done two things. First off, it's pasted the table, but it's also pasted this other square, and truthfully, I have no idea what that is. It's invisible. I'm going to click off to the side and then try to come back and click the square and get rid of it. Doesn't really matter. And this one, I can simply resize it by dragging things over like this. That's not so bad. That one works pretty well. But the best way to do this by far, again, is to go into a spreadsheet. So I've got a spreadsheet here. I just press paste, and now you see it looks exactly like what we had in Excel with the empty columns in between, except this time the column names are in the right place. And so if you have tabular data, you can put it directly into a Word document, a Google Doc, a presentation, but it works best to put it into a spreadsheet, which allows you to manipulate the tabular data. But often, instead of a table, people are more concerned about sharing the graphics. So let's go back to Jamovi for a moment. And when I click on that, I'm going to come down and I've got a graph. I actually have several graphs here. Let's take this one right here, pedal length. And I'm going to do an option click on this, a two-finger click on my Mac. And I can save it, and I can save it as either a PDF or as an HTML like I did with the earlier ones. And it's going to look exactly the same. But I want to show you how to copy and paste it. I'm going to go copy. It says it's been copied. Now let me go back to Word. I come here into Word. I click down here. I scroll up a little bit. I press paste. Beautiful. It looks fabulous, and we're good to go. And obviously, if you want to, you can resize it. I can click on that and drag it down a little bit. Similarly, if I want to work in PowerPoint, I can just open this up and I can go to a new slide and I can paste it. And there it is. And it wants to give me lots of abilities to animate and stuff. I will click that. But that's a great way to share your information. It's big, it's clear, it's nice. By the way, these have transparent backgrounds. So if you put it on a slide with a different background, it'll show up that way. And so that's a nice way. Just copy and paste. Things work a little differently in Google Docs and in Google Slides. And let me show you how that works. I'm going to go back to my browser here, and I'm going to try to paste in this image. I'm going to come down here, and I'm going to press paste. And what happens is it says unable to create some images, dismiss, and it acts like it's doing something, but it's not going to get anywhere. So I'm just going to delete that. And the same thing happens in Google Slides. The easiest way around this is to do a small intermediate step. And actually, this is a good thing to know how to do anyhow. Let's go back to Jamovi. And I'm going to take this graph, I'm going to right click on it, and instead of doing copy, if I'm going to go into Google Docs or Google Slides, I'm going to want to save it first. Now, by default, it wants to save it as a PDF file. And then what's actually nice about that is PDFs are infinitely scalable because they're vector graphics. That's nice. But I don't want to do that for this one. I want to save it as an image file. So I'm going to come down here to format, and it can save it either as a PNG file, a PNG file, which has transparent background. That's the kind I usually use. But you have two other options, the SVG and the EPS. And so depending on the programs that you're using, you may want to use one of those others, but I like the PNG, even though it's now of set resolution. So I'm going to come right here, and I'm going to save it as graph.png. And now I can go back to my document here, and I can come down to my downloads folder, and I just drag it in. And there it is, and I can do the same thing in my slide. I'm going to come right here to my slide, and I'm going to go to my folder and drag in, and I'm going to center it. And there you have it. I have now successfully imported both tables and graphics into Microsoft Word and PowerPoint, the table into the spreadsheet, and similar things for Google Docs, Google Slides, and Google Sheets, although the way you go about it is sometimes a little bit different. But all of these make it possible for you to take the analysis that you've worked very hard on in Jamovi and find a way to share your insights, find a way to share the possibilities you got in your data with other people. In our next chapter on t-tests in Jamovi, we're going to go from the piece to the whole. That is, we're going to start with inferential statistics, which allows us to describe a sample of data that we have in front of us, and then use that to describe a population, something larger and more than what we observed. We are using the sample to infer things about the population. And the t-test is the simplest and most direct way to get started with this. In this chapter, we're going to talk about three kinds of t-tests. First, we'll look at the independent samples t-test that you use to compare two groups' means to each other. The second is the paired samples or repeated measures t-test, where you're looking for changes in scores from time 1 to time 2 for one group of people. And third is the one sample t-test, where you're taking one sample's mean and comparing it to a known population mean. Taken together, the three of these serve as an excellent introduction to the concept of inferential statistics and going from the specifics of your sample at hand and generalizing to the population at large. One of the simplest inferential tests that you can do is the independent samples t-test. This is where you're comparing the means of two different groups. Very easy to do in Jamovi, and you can actually do several variables at a time, although they're going to be separate comparisons. To show you how this works, I'm using the example dataset bugs, which talks about how much people want to get rid of bugs that are either low disgusting, low fright, low disgusting, high fright, through high disgusting, high fright. And it's rated on a 0, not at all, to 10, very much scale. And we have information about people's level of education, the region they live in. Gender is coded as male and female. And so I'm going to use the gender one and compare the male and female respondents on these 4 different variables. Now, before you do a t-test, before you start doing inferential tests, it's a good idea to take a look at the variables and to see how well they meet the assumptions. Because certain things like normality or similarity and variance are important for a t-test. So I'm going to come over here to exploration and descriptives. And then I'm going to pick my 4 outcome variables right here. I'll put them here under variables, and then I'm going to split the whole thing by gender. It's not really the table that I'm most worried about, although you can see that we have more female respondents than male. It's not a big deal. And the means are, well, there's a 1 point difference, there's a 2/3, there's a 1/2 point. So they vary. What I really want here are the plots. So I'm going to come over here to plots, and I'm going to get a density histogram or density chart and box plots for each of these comparisons. And so what you see is these ones are kind of sort of close to normal. These are female respondents here. These are male respondents here. Distributions are pretty similar. The box plots show there's no outliers. There's a lot of overlap. Okay, here's where we start getting non-normal distributions, which is in a sense a problem, but because of the central limit theorem and because we're really working with sampling distributions, it's not the end of the world. We can still go ahead and do things. We've got a couple of outliers. Similar distributions. Okay, so now we see a little bit what's going on. So with that as context, I'm now going to do the regular t-test. And so I'm going to come over here to t-tests and do independent samples t-test. And all I need to do is pick my dependent variables, or you can just call them outcome variables. Dependence usually for when it's a randomized experiment. And then the grouping variable is the thing that I want to split them into 2 different groups on. I'm going to use gender here, so I'll click that over here. And it gives us this table by default, and it's going to give us the t-test and the p-value, which is for the significance test. And we can see from this right now that actually there are no significant differences between the male and female respondents on any of these. The closest we had was a p-value of 0.161. And the rule of thumb is it needs to be less than 0.05 to be considered statistically significant. This one down here is a lot closer. It's 0.06, nearly significant. That's this last comparison right here. But there's a lot more you can get from the t-test function in Jamovi. And so I'm going to do a few of these things. Now, if you are familiar with Bayesian statistics, Jamovi can incorporate that. It's kind of nice. I'm going to come over here and get the mean difference. So that's the mean of the women minus the mean of the men. And you can see they're about 0.55 points, 0.606. Okay. I'm also going to get the confidence interval, which by default is set at the 95%. And if I scroll this over a little bit, you can see the whole thing. And also you can see that they're negative on one side, positive on the other. So they include 0, which is consistent with the differences not being statistically significant. I'm also going to get the effect size. And in this case, it uses Cohen's d, which tells you how many standard deviations there are between the 2 groups' means. And in this case, they're pretty small, from close to 0 to the biggest is 0.4 standard deviations. I'm also going to get normality checks. So we know that the distributions are not entirely normal, meaning bell curve shaped. And the test that we have here is the Shapiro-Wilk test. And it lets us know that really none of them are exactly normal. We could tell that by looking at them, but again, it's really not the end of the world because we're using the sampling distributions and not the raw distributions. I'm also going to check for equality of variances. That's something that's also important for the t-test. It says that the 2 groups need to be spread out approximately the same amount. And this is going to use Levine's test for the equality of variance. And you can see on this one, none of these are significant. In fact, they're all really 0.4 is the lowest. And so there's no significant difference in the variability of the 2 distributions, which is what we want. I'm also going to click descriptives. And that's going to give me the means and whatnot of each of the groups. And so you can see the mean, the median, standard deviation, and the standard error, which is used in the inferential tests. And then finally, the descriptive plots. And in this case, what it gives us are confidence intervals for the means, as well as it shows the median for each group. And since these are the ones that correspond most closely to the inferential test of the t-test, it's probably the best one for actually seeing whether there's a difference. The general rule of thumb here is that if the confidence interval, that's this vertical line for one group, overlaps with the mean of the other group, then they're usually not significantly different. And we got a lot of overlap here, a lot of overlap. And these ones are pretty separate, and so this one was nearly significant. Anyhow, that's how you can do the independent samples t-test using a single categorizing variable. In this case, I used male and female respondents. And you can use several outcome variables simultaneously, and it's an excellent first step in getting a look at what's happening in your data through inferential statistics. Sometimes you have data from one group of people and you're comparing them either before and after some kind of intervention, or you're comparing them on two separate measurements and you want to compare each person's score with their own score. So you're looking for changes from one variable or one time to another. This is when you want to use a paired samples t-test, and it's very easy to do here in Jamovi. For this example, I'm using the same bugs data, which talks about how much people want to get rid of bugs or insects that are low disgusting, low fright, up to high disgusting, high fright. And it goes from 0, which is the lowest, to 10, which is the highest. I'm going to come up here and I'm going to use paired samples t-test. That's the test that we're doing here. And what we have to do is we have to specify pairs of variables. Now, there are a few different ways that you can select the pairs that you want to do. So for instance, you can click one variable and push it over here, and then you simply click the second variable. So maybe I'll do this one. And so that sets up a pair. You can also click one and do a command or control click and select the other. So you get both of them there at the same time, and that gets a pair. Or if you have a bunch of comparisons all in a row that makes sense to do, you can select the whole thing by just doing a shift click. And what it's going to do is it's going to put the variables together in order. So number 1 goes with number 2, number 3 goes with number 4, and so on. Now, what I have here, by the way, is a violation of the independence of observations. Normally, you wouldn't want to be doing the analysis quite like this because we're looking at the same comparisons in different ways. This is more like a post hoc test from an analysis of variance, but the procedures for doing this are the same. And so it's a valid demonstration of the process in Jamovi. So what I have right here are my 4 pairs of variables. And you can see that right over here, it's done all the tests already. And we can see that in fact, all 4 comparisons are statistically significant. So in one sense, that's the simple thing, and we can stop right there. Fortunately, Jamovi gives us some other options. I want to take a quick look at them. Let's look, for instance, at the mean difference. How big is the difference? Or rather, we also want to look at the mean difference. And what that does is it gets the difference between the first variable and the second variable for each person. That's a difference score. And then it gets the average of that difference. And so here we have the differences, and you can see these ones went down across the comparison. This one went up. By the way, whether it's positive or negative is arbitrary. It's simply a matter of which of these you put first and which one you put second. And we have the standard error. I'm also going to get the confidence interval for the mean difference. I got to scroll over a little bit so you can see that. We'll get the effect size, which is Cohen's d. And in this case, it says how many standard deviations there are between the scores at time 1 and time 2, or the scores on the first variable and the second variable. Really what it is the mean of the different scores divided by the standard deviation of the different scores. And you can see these ones are actually pretty big. That's almost a full standard deviation. We can also get descriptives, which gives us the means and the medians of the variables independently. We can do a normality check, which can be important because the t-tests are valid when they are working with normal or bell curve shaped distributions. On the other hand, not really the raw distribution that's important here, but the sampling distribution. And that's a slightly different thing. And even though we have some statistically significant things here, I usually don't personally worry about it very much because it's the sampling distribution. As long as you have a large enough sample, and we're pretty good, you're probably okay. I'm going to finish with the descriptive plots, which give us confidence intervals for the differences. So I'm going to wait a second here while it updates. And then we'll scroll down here to the plots. And so what this shows us are the mean and the confidence interval for each of the variables in the comparison. So this is low disgust, low fright, and high disgust, high fright. That's the biggest difference available in the data. And you can see they're very far away from each other. There's no overlap at all. The square is the median. And what's funny here is you can see the median is actually above the confidence interval because we had a ceiling effect there. People gave really high scores to that. And the mean's only lower because there were outliers on the low end. And you can see similar distributions for some of the other ones. And so this is a good way of making comparisons for the same group of people on one variable versus another, where they're looking at two different things, or often when you're doing something before and after a particular intervention. The simplest version of the t-test is the one sample t-test, which allows you to compare the mean of a single group that you have data from to a chosen hypothesized value. It might be a national average. It might be a theoretical value that represents the baseline against which you want to compare everything. Now, this is really easy to do in Jamovi. Here I'm using the example dataset Big 5, which contains a number of ratings where people evaluate themselves on 5 major personality characteristics: neuroticism, extroversion, openness to experience, agreeableness, and conscientiousness. And these are all rated on a 1 to 5 scale. And I want to show you how we can evaluate all 5 of these simultaneously. But before you jump into t-tests, you always want to do some exploratory analyses to see if your data are going to work well with the intended analysis. So let's go first over here to exploration, and let's go to descriptives. And what I'm going to do here is I'm going to pick the 5 variables and put all of them into the variable list. By the way, Jamovi updates frequently. And in fact, from the time that I started this morning and I'm finishing it now, it's updated. And we have a few extra options available now under descriptives. So here we have the mean, the median, the minimum and maximum by default. I also want to get the standard deviation. And I may also want to get, for instance, a normality test. And this is one of the new features. This is just a p-value that lets us know whether something is normal or not. And so this one is nearly not normal. This one's far away from normal, and so on and so forth. The important thing here actually is going to be the graphics, and I even have some more choices here. I'm going to do a density chart, like a histogram, smoothed out. I'm also going to do box plots, which are good for identifying outliers. And then I'm going to do the new option here, which is a QQ plot, which stands for quantile plot. And it shows how well the observed data match up against, for instance, a normal distribution that has the same mean and standard deviation as the observed data. So I'm going to click that as well. And the charts look a little different. They're colored differently, but here we have neuroticism. That looks basically normal. And the box plot shows that it's basically symmetrical with a few high outliers. The QQ plot, it shows information on a diagonal. And if all the dots were exactly on the diagonal, that would tell you that the distribution matches what you would expect from a normal distribution. We're really close here. We have some small variations at the tails, which is how it normally works. Extroversion, you see it's a little bit skewed. We got some low outliers, and you can see that happening here at the bottom. Openness is symmetrical, though it's slightly funny looking. You can see how it tapers off here and here. But these are not major deviations. They're statistically significant because it's a large sample. Here we have some low outliers on agreeableness because most people want to say that they're really agreeable. And then conscientiousness, same general idea. And so that's some of the important background. And what I saw here is nothing really worrisome. And this is just confirmation that our data probably work well with the assumptions of a one sample t-test, which includes normality, and we can go ahead and do our analysis. So now I'm going to come over here to t-tests and click on one sample t-test. And when I do that, I can select my variables. I'm actually going to select all 5 of them simultaneously. You only want to select multiple variables if they have the same null value that you're comparing them to. Now, a lot of times that null value is going to be 0. That's a silly thing to do in this case because 0 is not even in the scale. These are rated on a 1 to 5 scale. And so what I'm going to do is I'm going to come down here and I'm going to change the test value from 0 to 3, because that's the midpoint of a 1 to 5 scale. And when I do that, you see how this table over here updates. It's doing students t-test. It's a one sample t-test. And you can see that all of them, the mean is significantly different from 3. This is not a surprise because most of these, there's a positive or a desirable end of the scale. People want to be agreeable. They want to be open. And so we tend to have high values. But I'm also going to look at the mean difference. How far away are each of these variables means from the hypothesized value of 3? And you can see they're not really big differences, 0.2 of a point, about 0.6 of a point. We're going to get the effect size for each one of these, which compares how far the mean is of the sample data to the population mean divided by the standard deviation. And here, because the standard deviations are not big, this value Cohen's d, the common effect size for this, is pretty big. For instance, openness is 1.7 standard deviations above the hypothesized mean of 3. That's a big effect. We can also get the confidence interval for the mean difference, which is going to add a few columns here. And you can see that it's all positive because our means are above, except in the case of neuroticism, because people don't want to be neurotic. We can also get a normality check, which is going to put this separate column here. We have a Shapiro-Wilk test. And these p-values here are what we had up at the top table when we checked off under descriptives. So that actually is a more convenient way to do it. I'm also going to do descriptives, which repeats a lot of the same information we had before, but sometimes it's nice to have it down here. An important thing is to look at the SE, the standard error, which is the standard deviation divided by the square root of the sample size. And you see that these are tiny, tiny values. They are 0.02 of a point. And that is what leads to a very funny descriptives plot, which normally shows you a confidence interval for the mean. But when our standard error is microscopic, you end up with invisible confidence intervals. In each case here, the circle shows the mean of the variable and the square shows the median, and they're super close. And you can tell, for instance, that openness is a little higher, even though at this point the labels don't automatically adjust, so they're a little squished together. But this lets you know that, yeah, everything's different from 3. 3 would be straight across right here. 4 of them are above, 1 of them, neuroticism, is below. But this is a very compact and concise way of looking at several variables simultaneously. And if you're simply trying to get a first quick look at how your sample data matches up with some expectations about the population, then this is a very good and quick way to go. In our last chapter on the t-test, we looked at methods that allow you to compare two things at a time, two groups where you're looking at the mean differences between them. But what if you have more than two things you want to compare, or maybe you even have a whole bunch of different groups that you want to compare, and you're trying to get insight into how those groups differ and how they affect the outcomes that you're interested in? Well, in that case, you're going to want to use the analysis of variance, also called ANOVA or ANOVA. And in this chapter, we're going to look at a few variations on the ANOVA theme that Jamovi makes available to us. The first is the standard factorial ANOVA. This is where you're looking at how one factor, a categorical variable that splits people into different groups, influences your quantitative or continuous outcome variable. You may have one factor, you may have several factors simultaneously. We'll also look at the repeated measures analysis of variance, where you're looking at people across more than one measurement time. Then we get into some things that really are rather sophisticated, the analysis of covariance, ANCOVA, and the multivariate analysis of covariance, where you have several outcome variables and you have some quantitative variables you're putting into the equation as well. It's an amazing thing that Jamovi makes these available, and it makes them easy to work with. And then finally, we'll look at a couple variations on non-parametric analysis of variance, where instead of making analyses based on means and standard deviations, we're looking at ranks. And taken together, all of these variations on the analysis of variance give you a much broader range of situations that you can analyze and a lot more potential for getting insight out of your data. And so let's take a closer look at the analysis of variance. Certain fields of research tend to use different methods. So for instance, if you're doing economics research, it's very common to use linear regression. If you're doing experimental research, it's extremely common to use the analysis of variance. That's also called ANOVA or ANOVA. And what it lets you do is it lets you compare the means of two or more groups, also breaking them up by one or more categorical variables simultaneously. To demonstrate this in Jamovi, I'm going to use the built-in example dataset tooth growth. Now, it's a curious topic. It's about the growth of teeth in guinea pigs who were given one of two different supplements, either vitamin C, which is shown here as VC, or orange juice, which is written as OJ. And then it comes in three different doses, 500, 1,000, and 2,000. I assume it's milligrams. And they're looking at the length of the teeth. That's len here. And what we can do is we can look at the combined effect of the supplement and the dosage to see how those jointly, as well as separately, affect the tooth growth in these guinea pigs in this experiment. But before we get started with the analysis of variance, we need to do a little bit of background work. This is always an important first step. And we need to look at the variables, both the outcome variable len all by itself, and then breaking it down by the categories that we're going to use in the analysis of variance. So I'm going to come over here to Exploration and click on Descriptives. And all I'm going to do here is I'm going to come down and select len for length. And I just need a little bit of basic stuff here. We have 60 observations total. We have a mean, median, minimum, and maximum. Great. What I really want though are the plots. So if this isn't open already, you just click on it to get plots. And I'm going to get the density chart, which is like a histogram, a box plot, which is good for showing outliers, and a QQ plot. That stands for quantile plot, which is a way of assessing how closely the observed distribution matches a theoretical bell curve or normal distribution with some of the same parameters. And so when I scroll down here, I see that len, length, is, well, it's basically unimodal. It's not exactly a normal distribution, but it's not pathologically different. See, it's symmetrical in the box plot. There are no outliers. And the quantile plot is a little funny, kind of waving around. If it were a perfect bell curve, every point would fall exactly on that diagonal line, but it's not too far off. It's not going to cause any real problems. On the other hand, I also want to break it down by the groups that we're going to use. So I'm going to close this dialog and I'm going to do it again, except this time I'm going to take len, that's my length, that's the outcome variable. I put that there, and then I'm going to split it by both sup and dose. That's supplement and dosage. And it's going to give me a really long table here where it's breaking down the n for each of these and the number of missing and so on and so forth. And while that might be really important, we'll get a condensed version of it later. What I really want right now, though, are the charts. Again, I'm going to ask for density and box plot and QQ plot. If I scroll down, and I'm going to move this over just a little bit so we can see more of it. What I have is paneled density plots. So we have here orange juice, which conveniently is in orange, and VC for vitamin C on the bottom. And we see, yeah, they're not really perfect normal distributions. I mean, this one's kind of close. The other ones are a little wavy. On the other hand, that's because they're also very small samples. There's not many observations within each category. But they're not, again, they're not pathologically different. We see we have some outliers here in the box plots. There's an outlier right there. That's for vitamin C at a 1,000 milligram dose. And there's another one for OJ. But again, not terrible. And then here are the quantile plots. And we don't have many observations in each group, so we have the dots are easy to distinguish. But again, not horribly different. So I think we're pretty good and ready to go ahead with the analysis of variance because we seem to meet some of the core assumptions of the technique. So what I'm going to do is I'm going to come over to ANOVA or ANOVA for analysis of variance. And I'm going to click this first one, analysis of variance or ANOVA. And what you have here is an option to do either what's called a one-way or one-factor analysis of variance. That's where you have a single variable, like for instance, supplement, and you're looking at how that affects the outcome variable, len or length in this case. But you can also put in more than one category, and you can look at the interaction between them. Because that's the most common approach in many fields, especially in experimental research, that's what I'm going to demonstrate here. So I'm going to take len and put it into dependent variable, and I'm going to take sup and dose. I'm going to do a shift click to get both of them and put them over here, and it puts it under fixed factors. And you can see the analysis of variance table is there and it's filling up. And we get our immediate results. We see that, for instance, the supplement, if I come way over here, that's a big value for F, and the probability value, which is used for statistical significance testing, is really low. It's less than 0.05, which is the common cutoff for statistically significant findings. So we have a significant main effect, meaning supplement makes a difference on the tooth length all by itself. Same thing is true for dose. In fact, it makes an enormous difference. You can see that the F value of 92, it's going to be much less than 0.001. And then there's also an interaction. So we're going to want to get a little more detail about all of these. The first thing I'm going to do is I'm going to get an effect size. The effect size that's generally used for the analysis of variance is called eta squared. That's this little Greek letter that kind of looks like a lowercase n. It's an eta. Now, if we had a one-way analysis of variance, we could do the regular eta squared, but because we have these interactions, we should do what's called a partial eta squared, which looks at the unique contribution of each of these factors. That's what showed up right here. We have an n squared p, partial eta squared, and it goes from 0 to 1, and it can be interpreted as the proportion of variance in the outcome variable len that can be associated with that particular factor. And we get a lot for sup. We get 22.4. For dose, we get a huge amount, 77.3, and then we have this 13.2. And again, these don't add up to 1, but they give you an idea of the relative strength of each of these things put together. What I'm going to do then is I'm going to go through some of the options. Now, you can specify the specific model. I'm using the very general approach, which looks at the two main effects for the two categorical or nominal variables that I'm using as predictor variables and their interaction. That's how I want to do it. So I'm just going to leave that alone. I'll close that. The assumption checks homogeneity tests because your different groups are supposed to have approximately the same amount of spread in the outcome variable. So I'm going to click that one. And that's going to bring up a new table here. We're doing the test for homogeneity of variance using Levene's test. And what we have here is the important part is this p-value at the end. It's 0.103, so it's more than 0.05, so it's not a statistically significant difference. That's good. We're also going to get a QQ plot of the residuals, or the variability in the data that's left over after we control for sup and dose and the interaction. And again, if it were perfectly uniform, which is kind of what you want, it would be right on the diagonal, but it's really close. So it looks like it meets the assumptions of the analysis of variance. I'm going to close that. Now you have an option of specifying specific contrasts in your design, especially if you don't want to do just this omnibus main effect interaction. This is a more complicated procedure. I'm not going to get into it except to let you know that it's there, and you have several different choices for how you make those contrasts. I'm going to close that and come to post hoc tests. And this is when you find a significant effect, you need to determine where it is. Now it's easy if you only have two levels or categories within your nominal variable. So for instance, for sup, we just have orange juice and vitamin C. So if there's a difference, we know that's where it is. But for dosage, where there are three levels, 500, 1000, and 2000 milligrams, you don't necessarily know exactly where they are. And it's more complicated with the interaction where there are 6 possible groups there. And so what we're going to do is I'm just going to select all of these and move them all over to the right. And we're going to get a big table that looks at possible cell by cell comparisons. Now it is a lot, and you get to choose the correction. A lot of people use the Scheffé or the Bonferroni. I personally prefer the Tukey test. That's from John Tukey, who developed it. And what we see, for instance, is that OJVC, well, there's only one comparison possible there. Yeah, that's significant. For the dosages, we see that all 3 of them are significantly different from each other. And then the interaction, it gets a little more complicated, mostly because there's a lot of possible comparisons here. But you see that not every one of them is statistically significant. We have a few that aren't. But that's going to be a lot easier to figure out if what we do is we look at the charts. We got the descriptive plots. And so what I'm going to do is I'm going to take the supplement and put that on the horizontal axis and the dose and make that separate lines. And then we'll get a 95% confidence interval. And we come down here. It sometimes takes a second for Jamovi to catch up. What you have here is orange juice on the left, vitamin C on the right, and the 3 dosage levels. This is 500 milligrams, 1000, and 500. And what we see here is that, yeah, the 500 is the lowest. Orange juice a little higher than vitamin C. That the 1000 is definitely higher on both of those, but about the same amount. But things flatten out when we get to 2000. In fact, there's no difference between orange juice and vitamin C at 2000. And there's really no difference between orange juice at 1000 and 2000. And so that lets us know really where the important differences are in the data. Now, the last thing is we have a couple of additional options and we can get the descriptive statistics. Now, this is going to mirror to a certain extent the statistics we did at the very beginning when we were checking things out. But it's going to create this small table that looks at the 2 variables, crosses them with each other, and gives us really the bare minimum, the number of observations within each cell, the mean for that particular cell, and the standard deviation. And now you have the data that actually is shown in this chart right here. So for instance, we have this 7.98 and a 13.23 way down low. And you can do some more detailed analyses there if you want. And so this is the walkthrough of the analysis of variance in Jamovi. Again, what we did is the preliminary work by looking at the outcome variable all on its own, then breaking it down by the categories that we were using to predict it, in this case, what the supplement was and what the dosage was, and then doing the analysis of variance with interactions and several of the options that Jamovi gives us. Makes it very simple and is a good way to break up your data to get the results, especially of an experimental analysis. Anytime you're analyzing data, you are making comparisons. You may be making them explicitly or you may be making them implicitly. The comparison that's usually most important in research is, for instance, a control or baseline condition versus some sort of experimental or manipulated or intervention condition. The idea is that if people are randomly assigned to one condition or another, then the differences between people balance out and you can look at the effect of just that manipulation. But a really interesting and powerful alternative to this, powerful meaning statistically powerful, easier to find the effect with fewer people, is what's called a repeated measures design. And this is where everybody in your study gets to serve as their own control, their own comparison or baseline. And the way you do that is by gathering data from them in more than one condition. If you have 4 conditions, you get it in all 4 conditions. And then you compare the change from one condition to another for each person. Again, a much more powerful design if your study allows for it. Now, the example data set that I want to use is the bugs data set. And this is where everybody in the study was asked to make evaluations about bugs in 4 different categories. Bugs meaning insects. And they looked at insects that were either low on disgust and low on fright, low on disgust, high on fright, high disgust, low on fright, and high disgust, high fright. And the thing that they're being asked is, how much do you want to get rid of this bug? And it goes from 0, not at all. Butterflies are very pretty. Nobody wants to get rid of them. To high disgust, high fright, which might be really big cockroaches or something like that. And people want to get rid of them. And so what this means is that people are making evaluations in each of these different categories and they get to serve as their own control. And this allows for extra power, although it also introduces a lot of additional complications into the analysis. One of the nice things about Jamovi is that it actually has the ability to do this kind of repeated measures analysis of variance. In other programs, that functionality may not be there, or you may have to pay extra for it, but here we have it built in right away. Now, as I do in all the analyses, before you do the actual analysis, you want to do some of the background checks. So let's take a quick look at these 4 variables, these outcome variables. I'm going to come here to Explore and Descriptives. And even though we've looked at these in other videos, it's worth doing them again right here. And we're going to get some statistical summaries, but I actually find it a lot easier to use the plots. And so I'm going to come down here to histograms, actually. And so I'm going to come down here to density and click on that. Now, unfortunately, I can't get side-by-side density plots for each of these. I would like that. And maybe that'll be available in a future version of Jamovi. But right now, what I can do is I can look at these distributions and I can compare them one to the other. What we have here is low disgust, low fright, where you see it bumps up against 10, but it goes all the way down to 0. Low disgust, high fright, almost nobody goes down to 0. We get things a lot closer to 10. High disgust, low fright, again, pretty close to 10. And then high disgust, high fright, basically everybody wants to get rid of those bugs. But now what we can do is, instead of looking at the distributions overall, we can look at the changes from one to another. So what I'm going to do is I'm going to come here to the analysis of variance, or ANOVA or ANOVA, and I'm going to select repeated measures ANOVA. Now, the way you set this up may not be immediately obvious if you haven't done this before, because you have to specify how the various measurements fall into the categories or the overall groups that you want to combine. So it's asking for my repeated measures factors. And what I have is disgust and fright. And so I'm going to double click on this first thing right here, and I'm going to write the word disgust. And then I hit return, and it asks me, what is the first level of disgust? And I'm going to call it low disgust. Because it might not be high and low. You might be doing right or left or up or down or something like that. And I'm going to do that for the next one. Now I'm going to skip over level 3 and go to RM, repeated measures factor 2, which is fright. And for that, I put low fright and I put high fright. By the way, you see that it's filling in over here, and it's also coming down right here. And what it wants me to do right now is to come over and find the variables that correspond to the combination of these factors. So which cell, which variable has the outcome for the low disgust, low fright? Well, fortunately, it's abbreviated. That LDLF stands for low disgust, low fright. So I just drag that over. And then low disgust, high fright goes right here. High disgust, low fright, HDLF goes there. And then finally, high disgust, high fright goes right down here. And so now it knows where the data is, and it knows how to parse them into the variables that we're interested in. And it does the analysis right here. Now, if we want to, we can put in a between subjects factor like gender as well. That makes it a lot more complicated, so I'm going to leave it out for right now. But what you see here is that disgust changed how much people wanted to get rid of the bugs. Fright changed how much they wanted to get rid of them. And there wasn't really an interaction between them. So disgust and fright didn't depend on each other. And so that is our initial result, but we have a lot of options with the repeated measures analysis of variance. So I'm going to scroll up here a little bit. Again, if I had a between subject factor like gender or where people lived, I could put that in here if I wanted. And if I had a covariate like a person's age or their level of exposure to bugs, I could put that in there as well. I'm just going to come down here and get an effect size. And for a study like this, it's good to get a partial eta squared. This little letter here that looks like an N is a Greek eta, and it's the common measure of effect size for the analysis of variance. And here we can see, for instance, that this 0.123 means about 12.3% of the variance in a person's response can be attributed to the variations in disgust. Over twice as much can be attributed to variation in fright, and that there's just 2.4% that's associated with the interaction. That's negligible. And then I can come down and I can specify the model. Now I'm just going to use the regular built-in main effect interaction model. So I'm not going to change that at all. I can look at assumption checks. Now, in the repeated measures analysis of variance, a common test is what's called sphericity. And it's sort of the repeated measures version of a normality check. And I can click it, but it's not going to be really relevant because what you find is that we only have 2 levels in each of these. We have high and low disgust, high and low fright. So it's always met when there's only 2. If we had 3 or more, then this would be important. So I don't really need that. Now, in a normal analysis of variance, I could also do the equality of variance test. In fact, I'm just going to click on that right here as Levine's test. But, it's irrelevant for this one because I don't have a between subjects factor like gender. So we can ignore that one. I can do post hoc tests if I want. And so I can, for instance, look at disgust and fright, and I can put them over here. It's not really necessary to do the post hoc test because I only have 2 categories within each one of them. And so it's obvious where the difference is if we look at the means. But if you had more than 2 categories within each factor, this would be something that would be important for you to do. I just want you to see how it works. You also have the choice of the correction that you do. The Scheffé and Bonferroni are very common. I prefer the Tukey test. And we can scroll down and we can see it's calculating all sorts of things. And these 2 correspond to the analysis of variance results we had earlier. And it's going to look at these specific comparisons. It makes for a very long table. And what it's telling us is that several of our comparisons, these first 3 are all significant and the last one, but not the middle 2. And that's a lot easier if you were to go back and have a means chart, but it gives you the means and you can look at specifically these possible comparisons. Now, the last thing we can do is we can come to estimated marginal means and we can look at the effects. So I'm going to come right here and do disgust, drag it right there. I'm going to get a new term and I'm going to get fright and drag it down right here. And we're going to get a marginal means plot. I'll also get a marginal means table. And I can scroll down and this is going to make it a lot easier to see what's happening in our data. Surprisingly, when a bug is disgusting, people want to get rid of it more than when it's not. And here are the numbers to go with that, as well as the 95% confidence intervals. And when a bug is frightening, they want to get rid of it. And you can actually see that the difference for frightening is much bigger than the difference for disgust. And then we get the numbers right there. And so this is really the collection of information you can get from the repeated measures analysis of variance in Jamovi. Some of these options aren't really necessary when you have just 2 groups within each factor or when you have a simple interaction. But even with more complicated designs, it's nice to know that the options are there and available in Jamovi to allow you to use the more powerful repeated measures design to find out what's going on in your data and start getting insight into your results. Sometimes when you're looking at the differences between groups, you both want to compare their means, but you also know that there's another variable, like a quantitative variable, that's associated with the outcome you're interested in. And if you want to put that in, one common choice is to do an analysis of covariance or an ANCOVA. And this is actually really easy to do in Jamovi. For this example, I'm going to be using the IRIS dataset from the example datasets. And I'm using this because we have 4 quantitative or continuous variables, the sepal length and sepal width, petal length and petal width. And we have a categorical or nominal variable species with 3 different groups. And that's a situation where you really would want to use an analysis of variance, but we can throw in some other measurements to try to predict something. So what I'm going to do in this particular example is I'm going to look at the sepal width. That's one of the 4 measurements of the flower of an iris. And before we get started, it's a good idea to explore what that variable looks like. So I'm just going to get sepal width. And I can put it right here under variables, and it's going to give us some descriptive statistics over here. I may ask for standard deviation also. That's helpful. But mostly I want some plots. I'm going to get a density plot, and I'm going to get a box plot to look for outliers. And that's going to give me my first take on the outcome variable, or the thing that I'm trying to predict. We see that we have 150 cases. The mean is 3.06, I believe it's centimeters. Median's close to that. Standard deviation is about 0.5 centimeter. And here is the distribution of all 3 species of iris put together. It's kind of cone-shaped, but it's unimodal, and it seems to be pretty well behaved. Here's the box plot. We got a few outliers on the high end, one on the low end, but it's pretty much a well-behaved distribution. And so if we're trying to model sepal width, this looks like a good variable to be working with. Now, when I'm doing the analysis of variance, I actually want to break it down by a categorical variable. And the one that I'm going to use in this example is the species. And so I'm going to do this analysis here over again. I'm going to go back to Explore and go to Descriptives. And I'm going to do sepal width again. But this time I'm going to break it down by species. Now I don't need any statistics, so I'm actually going to just cut those out here. Really, all I want at this exact point is the plots. And I'm going to do density plots where it's broken down by group. And here you can see the three distributions shown by density plots. They're like histograms, but smoothed out for the Setosa, the versicolor, and the virginica. It's three different irises. You can see we got a little bit of an outlier down here, and things are kind of bumpy over here. And so if we're trying to explain sepal width, knowing what species an iris is going to be a little bit helpful, because we can tell that Setosa is at least a little different from the others. And so let's do an analysis of variance, which would be a common way of looking at the difference between these. I'm going to close this and go to ANOVA. I'm going to do an analysis of variance, just a one factor or a one-way ANOVA, where I'm going to put sepal width as the dependent variable, and I'm going to put species as the fixed factor. And I'll just do a very basic one. Actually, I will get a partial eta squared. And then I will come down here to descriptive plots. And I will get species on the horizontal. And let's see if we have anything else here, some descriptive statistics. And that would be enough for right now. And what it's showing us here is that, yeah, there definitely is a difference between the three species on their sepal width. The value of P here, less than 0.001. In fact, the value of F of 49 is huge. And the partial eta squared is 0.40. So about 40% of the variance in the sepal width can be at least associated with the three different species. And you come right here and you see a really big difference when we're looking at just the mean with the confidence interval. But we might be able to do better than that by throwing in a covariate or a quantitative or continuous variable that is associated with the outcome, the sepal width, and maybe that would be helpful. So what I'm going to do actually is I'm going to do a little bit of exploration first. I'm going to come and do a scatter plot using the scatter module. Now, if you don't have the scatter module installed, you get it by coming over here to modules under Jamovi library, and you select scatter under here. And once you click install, it's going to be available right there. I'm going to use that one, exploration and scatter plot. And I want to look at the sepal width as the outcome. So I'm going to put that on the Y, but let's put the sepal length. By the way, a sepal is like a petal. They alternate, the petals and the sepals alternate as you go around the flower. And I'm going to put a smoother through it. As it's like a local regression line. It kind of follows the pattern in the data. And we'll even put the standard error on there. And so you can see that there is, in fact, an association between the two variables. And so maybe throwing in the sepal length would be a helpful thing. In fact, if you want to really see what's going here, you see how we have this nonlinear association? It kind of jumps up here and it comes down here. Remember, we have three different species, and there may be an important difference between them. So I'm going to come back here to exploration. I'm going to do a scatter plot again. That way I create another chart. And I'm going to put sepal width under the y-axis. I'll put sepal length under the x. And I'm going to do the smoother with the standard error. That's what I had before. But now I'm going to throw into it species as a grouping variable. And because I can, I'm also going to put density plots on the marginals. That means across the top and on the side that show us the distributions of each variable for the three different groups. And so when we look at this, I'm going to move this over a little bit. Actually, I'll close that first and move it over a little bit. Now you can see that there's a really strong association, that the Setosa iris has a very different association between sepal length and sepal width, and the other two are pretty similar to each other. So we have something important to work with here when we're trying to get the association. I could also do a linear association. In fact, because that's relevant to the analysis of covariance, I'll do exactly that. So I'm going to repeat this analysis. I'm going to do that same thing, but instead of using the curved smoother that goes through the data, I'll use a linear or straight line regression. So I'm going to come here to exploration and scatter plots, and I'm going to put width again on the y-axis, length on the x-axis, species on the group, and I'm going to put linear regression line with the standard error. And I'll still put, in this time, instead of doing densities, I'll put box plots just so you can see what that looks like when we run it. different way of looking at the data. I'll close this menu and bring this over a little bit. And now you can see that we have this really strong straight line association here. And this is where the analysis of covariance is important, because not only do the three groups have separation between them, which is something you would expect with the analysis of variance, but they have different slopes on the association. That's going to be an important thing for the analysis of covariance. And we have box plots for each of the variables, and they break them down by group. So we can see we have a little bit of outliers and a little bit of overlap between them. So let me now set up an analysis of covariance. And the way I do that is I come to ANOVA, and I come down to this third option, ANCOVA, which again is short for analysis of covariance. And what I'm going to do there is I'm going to take my dependent variable, the outcome, the thing I'm trying to predict, and that's going to be sepal width. I'm going to put that right here. Now the fixed factor is the thing that defines the distinct groups. That's going to be species. So I'm going to put that under fixed factors. And this so far is just like the analysis of variance I did earlier. But now I can put in a covariate, another quantitative or continuous variable that is associated with the outcome and may help me get a better understanding of what's happening. In this case, I'm going to use sepal length because we saw that there's an association with it. I'm going to put it here under covariate. And you see that the table expands slightly. And we now have two inferential tests. We have one for species. We get this enormous F ratio, 94. And it says, yeah, it's statistically significant. So there is, in fact, a difference on the species as far as sepal width goes. And we also see that the sepal length also has a significant association, even when the both of them are put in the equation together. We can get a partial eta squared here to look at the effect size. And we see that the species makes more of a difference, but they're still both really big, robust findings. Now let's look at some of the other options we have here. We can look at model, and I'm going to stay with the default model. If I want to put in an interaction, I can. And actually, now that I think about it, I will put in an interaction because these lines have different slopes. And so I'm going to select the two of these. I'm just going to do a shift and click to get both. Come right here and say, give me a two-way interaction. So that's going to add the species by the sepal length. And now you can see that that's interaction is also statistically significant. And again, it's because they have different slopes here in this chart. Now let's come down and check some of our assumptions. We can do a homogeneity of variance test because the three groups are supposed to have approximately equal variance on the outcome variable, the sepal width. And we can also get a QQ, a quantile plot of residuals. By the way, the homogeneity of test variance is not statistically significant. That's a good thing. It means that we are not violating our assumption. The QQ or quantile plot of the residuals assesses another assumption of the analysis of covariance, and that is that the residuals or the errors in prediction, how far off you are by your model, that should be approximately spread out the same for each of your groups, and it should be approximately normal, kind of a bell curve. If it were a perfect bell curve, every dot would be on this diagonal line, but you can see they're really close, so we're doing well. Now, it may be that you have a situation where you have specific contrasts you want to look at. So maybe you want to look at just setosa versus the other two kinds of irises. You can set that up here. I don't want to do that, so I'm just going to close that and leave it alone. I could do post hoc tests. That's where I look at the two, and because I know that one of them is different from the other two, I'm actually going to slide that over here. I can pick the correction. I'm going to stay with the default Tukey. And when I come down here, you see it's going to compare setosa with versicolor and virginica, and then versicolor with virginica. So there are three possible comparisons when you have the three different groups. And what you find is that the versicolor and virginica are not significantly different from each other. That makes sense because they overlapped a lot. But the setosa is different from the both of them. In fact, if we come back up here just for a moment, this is setosa over here. And this is the versicolor and virginica. You can see that they're very similar, but in setosa is pretty different. So that result makes sense. Let me scroll back down. And then in terms of descriptive plots, I can get a means plot by moving species to the horizontal axis and get confidence intervals. And that'll take just a second to pop up. it's confirming what we already knew, that the sepal width varies for our 3 different species. And under additional options, we can get descriptive statistics. We got some before, but I might as well just click it here because it puts them right next to the chart. And since they're the things that go into the chart, it's a little easier to put it all together. And so this is kind of an extended presentation because I spent time going through the preparatory analyses, doing the univariate exploration and then breaking it down by categories, and then doing the normal one-way analysis of variance, and then looking at the associations between sepal width and sepal length, and sort of building up the narrative arc of the analysis. And when we get through the whole thing, we see, yeah, there is in fact not just a difference between the 3 species, but also the relationship between the sepal length and the sepal width is different for the 3 species that we got by having the different slopes of the regression lines. And so it gives us some nuance. It gives us a little additional insight into what is even a very, very simple data set. And that's some of the power you can get from the analysis of covariance in working with your own data. Some of the options that Jamovi gives you in working with data are really kind of surprising because they're not usually found in other statistical software, at least not in the standard installations. So if you're working in SPSS and you want to do a multivariate analysis of covariance, you might have trouble. It may not be included there in the base package, or you may have to download additional things in other programs to make it work. But a sophisticated analysis like a Mancova is available as part of the base package in Jamovi. That's an amazing thing. Now, MANOVA stands for Multivariate Analysis of Covariance. And the multivariate part means you have more than one outcome variable, and you're trying to model the group differences on all of those simultaneously. Plus, because there's the C in the middle, that means covariance, and you could use a quantitative or continuous predictor. You don't have to, because you can do either of the above with a Mancova option in Jamovi. Let me show you how this works with the iris data again. All I'm going to do here is I'm going to see if there are group differences on all 4 of these variables. Now, I'm going to begin with the exploration, something I say that's always a good idea. So I'm going to come up here to exploration and go to descriptives. And what I'm going to do is I'm going to get these 4 quantitative or continuous variables, put them here, and I'm going to break it down by species, split it by species. Now, I actually am not concerned very much about the statistical table at the moment, so I'm just going to unclick all of this and close that up. What I do want is the plots, and I'm going to do the density. That's the, like a histogram, smoothed. It's going to break it down by the 3 groups so we can see what sorts of differences there are between those groups in the data. A minute for Jamovi to get there, but now what we have is the sepal length, and we're looking at the 3 different species of iris flowers. We have Setosa, versicolor, and virginica, and you can see that there are differences, that things go up a little bit as we go from one species to another. The pattern switches around a little for sepal width, where Setosa is the highest and the other 2 are really close. Petal length, we have an enormous difference with Setosa way down here on the low end, and the other 2 are still distinguishable. And then petal width, we actually have this nice separation between the 3 of them. And we can look at each of these separately. If we wanted to do 4 separate analysis of variance analyses, we could look at the group differences on each of these separately. The MANOVA or the Mancova allows us to do all of them at once, although I'll let you know, that sounds like it would be a big improvement, but it's often pretty hard to interpret the results because the math that goes into this gets much, much, much more sophisticated. But let's see what Jamovi can do to make this procedure at least a little more accessible. So I'm going to close this, and I'm going to come over to the ANOVA and come down to Mancova, which again stands for Multivariate Analysis of Covariance. And when I click on that, the nice thing is it's not giving me all the possible options you could get because there would be a million. But the easy thing is, what are the dependent or outcome variables? I'm actually going to pick all 4 of these flower measurements, put them over here, and then factors, that says what defines the groups, that's the 3 species here. Now, if I wanted to use one of these measurements as a covariate, or if I had something else with covariate, like the age of the plant or the height of the stem or something, I could put that in there too. I'm not going to do that because it doesn't change the output very much, and I just want to focus on what we have right here. The important thing is we really just have this one table. That's kind of all that it's giving to us. In fact, we have the same analysis really done 4 different times. When we come here to multivariate tests, the question that these 4 things are trying to tell us is, are there differences on these 4 variables simultaneously between the 3 different groups? And it turns out that all 4 versions of the math that goes into the multivariate analysis of variance or covariance, they're all giving us the same answer in this case. They're all saying that, yeah, there's this huge difference. It's a highly significant difference. The p-value, you're looking for something less than 0.05, is much less than that. It also does univariate tests, where it's looking at the variables separately. So we can look at sepal length. Again, this is the one factor or one-way analysis of variance. And we can see, yeah, there are differences between the groups on all 3 of them. Now remember, with the analysis of variance, it doesn't mean that every group is different from every other one. If we come back up to here, for instance, we can see that Setosa is different on sepal width, but versicolor and virginica are very similar to each other. And so there's a difference somewhere in the mix, even if not all 3 are different from each other. And that's what we get here. I'm just going to finish with one of the assumption checks. We can do the QQ plot of multivariate normality. Again, something that we're generally looking for, because a normal distribution or a bell curve is a good idea. And a multivariate normal distribution means that if you have one variable, that would be a bell curve. If you have 2 variables, it's doing it in an X and Y dimension, and you're looking for sort of a smooth hill. And if it's 3 or 4 variables, then you get into, higher dimensions, and it's really hard to visualize. But if we just look at the quantiles, that's what the QQ stands for, is the quantiles. We have the chi-squared quantiles across the bottom, and the squared Mahalanobis distance on the side, which is also a quantile. And the idea here is that if all the dots, those are our data points, fall on the diagonal line, then you have what is basically a multivariate normal distribution. We're really close to that, so I think we've met these assumptions. But really, the options that we're getting in Jamovi here are pretty simple for what could be an extremely complex and sophisticated analysis. Basically, it is telling us that, yes, you have a statistically significant MANOVA. I could call it a Mankova, but I didn't actually use a covariate this time around. And then it follows it up with univariate ANOVAs for one factor at a time. And it's enough for us to be able to say, yes, there's something there. And if you have the theory that says what the differences should be, you might be able to tell that by looking at some of the univariate analyses as well. And so the nice thing again about Jamovi is it makes this really sophisticated kind of question easy to answer. It gives you just enough information to get the yes, no that you're looking for if you're doing hypothesis-driven research. And that's going to be a very significant first step in understanding what's going on in your data. Each version of the analysis of variance that we've looked at so far in Jamovi has something in common, and that is that they all rely on population parameters or assumptions about population parameters, like the population mean or the population variance. So the 1-factor or 2-factor analysis of variance, the repeated measures analysis of variance, the ANCOVA, the analysis of covariance, even the multivariate analysis of covariance, all of them have this parametric assumption in common. It's typical among analyses, but there are other options. These are called non-parametric tests, and they're ones that don't make assumptions about population parameters. And traditionally, they're based on ranks. And so for the analysis of variance, the one-way version, the non-parametric or ranked version of it is called the Kruskal-Wallis test. And it's actually really easy to set up. If you're concerned about non-normal distributions, this might be a good choice. Now, I'm going to use the IRIS data. We've looked at it lots of times. And I'm going to look at the sepal width and break it down by the 3 different species. But let's take a quick look at the sepal width and break it down in a couple of different ways. I'm going to come over here to Exploration and go to Descriptives. And what I'm going to choose is sepal width as the only variable that I'm looking at. And I'm going to split it by species. I'm not really concerned about this great big table. But what I do want is the plots. There's two kinds of plots that I want to get. I want to get the density plots that'll split it by species. And I also want to get not the box plot, but this time I want to get the data plot. It's a dot plot. And I have a couple of options on that one. I can do jittered, which randomly shuffles them from left to right. Let's see if I come down here, if it's showing up yet. But I'm going to actually get the nice and orderly stacked version because it makes it a little easier to tell what we're dealing with. That was the jitter that popped up there for just a second. Stacked version. Now, let's take a quick look at these analyses. What you can see from this is that in terms of sepal width, the Iris setosa, their sepals are a little wider than the sepals on the Iris versicolor or virginica, which are pretty similar to each other. If we were doing a parametric test, we'd be looking at the means of each of these, and we've done that previously. But the Kruskal-Wallis looks at ranks, and in that case, you're sort of looking at where is the highest score. This is the number 1. This is the second highest, the third highest, the fourth highest. And if you go through, and as you come down to here, you have to start saying, well, this might be the 17th highest, and this one here might be the 34th highest, and this one is the 125th highest. You take every single data point across all three groups and you rank them. And so this one, I know there's 150 total. This will be the 150th right here. So we go from rank number 1 to rank 150. And the question is whether the ranks are evenly distributed across the three versions. That's the question that the Kruskal-Wallis test is trying to answer. So let's go and see how to do the Kruskal-Wallis. It's actually really simple. Just come to ANOVA. And then under non-parametric, go to one-way ANOVA where it says Kruskal-Wallis. And we click on that, and it's actually a very small dialog box. It only asks me for two things. It says, what's your dependent variable? What's the thing you're looking at? I'm doing just sepal width. And what's your grouping variable? And I am using the species of the iris. And I get this tiny little table that just has 3 numbers in it. It gives me the test statistic, which is actually a chi-squared. I know that looks like an X, but it's a Greek C. It's a capital chi with 2 degrees of freedom. And this is a highly significant result, meaning that these aren't even remotely close to identical distributions. Now, normally when you get a significant analysis of variance, you want to do some sort of follow-up with post hocs. And because we're using ranked non-parametric data, we need to do something a little bit different. And Jamovi gives us the option of the DSCF pairwise comparisons, which stands for Dwas, Steele, Critchlow, and Fligner pairwise comparisons. You can think of them as similar to the Chaffee or Bonferroni or Tukey, because what it does is it gets every possible comparison, and with 3 groups, there's 3 possible comparisons. It calculates a test statistic, and then this part here at the end that's important is the p-value that tells us whether it is statistically significant. Now, you can see this one's taking a while, and that's one of the things about when you're dealing with ranks, and especially if you have a lot of data, is an iterative procedure, and it takes a long time to get through all of it. But here we have it. And you can see that in all 3 cases, the p-value, the probability value of this happening at random, if the null hypothesis is true, is way less than the standard 5%. This is 0.5%. And here they're even lower. And so these all serve to reject the null hypothesis that everything is similar, or that the ranks are sort of randomly distributed across the 3 groups. And it gives us the same general impression that we got from doing the one-way analysis of variance earlier, that the 3 groups are not different. Obviously, this one's really high. These 2 are here. But even then, the rank shows us that there are still differences between these 2 groups because of the way the ranks are divvied up between them. And so the Kruskal-Wallis is a non-parametric or rank-based analog to the one-factor or one-way analysis of variance that you can use, especially when you're concerned about non-normality in your data. One final variation of the analysis of variance that's available in Jamovi is what's called the Friedman test, or a non-parametric analog to the repeated measures analysis of variance. The idea here is that you have several outcomes that you've measured for a group of people, and you're looking for changes across those outcomes. I'm going to demonstrate how this works with the built-in example data from bugs, where people who are rated on a number of demographic variables evaluate insects and how much they want to get rid of them, where those insects vary according to low and high disgust and low and high fright. And they rate it from a 0, meaning don't want to get rid of it all, to 10, want to get rid of it immediately. And we've done this analysis before with the standard repeated measures analysis of variance, but we can also do it with the ranked version, the Friedman test. And this is an advantage if you're worried about normality in your data. So most analyses like to have bell curves and normal distribution. If you don't have that, and we actually know that we have some non-normality in this data, then a non-parametric test might be an appropriate and informative choice. But let's begin by looking at the distributions of these 4 variables. We've looked at them before, but I'm just going to come here to exploration and descriptives. And then I'm going to pick these 4 outcomes: low disgust, low fright, up through high disgust, high fright. I'll put those under variables. And I'm not so much concerned about the statistics as I want the plots that we can get for each of them. So I'm just going to hit density. And unfortunately, I can't get them stacked right next to each other, which would be most convenient. But we can still compare going up and down in the list to see what we have. An important question is, are they normal and are they on the same scale? Now, this first one, low disgust, low fright, it's not exactly normal, but it's not terribly different. We've got a pretty strongly skewed distribution with the low disgust, high fright, also strongly skewed with the high disgust, low fright, and then really skewed with the high disgust, high fright. And so this is a situation where using a non-parametric test based on ranks as opposed to a parametric test that also assumes things like normality, this might be a good option. So let's close this and come over to the analysis of variance and drop down to the last choice here. It's under non-parametric, and it's the repeated measures ANOVA, or the Friedman test is what it's also called. And I click on this, and there's not too many options here in the Jamovi dialog, but there's enough to get what we need out of it. So what I need to do is I need to pick my measures that I'm looking at. And I simply pick all 4 of them. I click the first, I do a shift click on the last, and I move them all over. And in this situation, I'm not breaking them down into categories like disgust and fright like I did with the regular parametric analysis of variance, but I do this way. Now, I get this tiny little table, just 3 numbers, that shows us that there is in fact a significant effect here. The first number here, the 55.8, is under the chi-squared. That's the distribution that we use. And that's a capital chi. We have 3 degrees of freedom. And this deviates significantly from what we would expect at random. And so we do find a significant effect here. And if you want to, you can get pairwise comparisons. They're like the post hoc comparisons, the Bonferroni or the Scheffé tests that we get with other procedures. And what we have here is a comparison of each set of variables here. With the 4 variables, we have 6 possible comparisons. So low disgust, low fright to low disgust, high fright, that's statistically significant. And in fact, all of them are statistically significant one way or another. Let's get the descriptive statistics for these. This will be a very small table. And you can see some of that is similar to what we had when we got this information up here. It's just arranged differently. And then we can also get a descriptive plot. We can choose either means or medians, but since we've been talking about means, I'm going to leave it right there. And it's just a little dot plot. It's not showing us a confidence interval because that really works differently when you're talking about a ranked situation. And even though these are means, it still lets you know that all 4 of these are different from each other. And because of this paired comparisons using the Durbin-Conover test, we can tell that all of these comparisons are significantly different from one another. And so that's a very quick run through of the Friedman test, which is a repeated measures analysis of variance analog for using non-parametric or ranked data. And again, depending on how far your data deviate from normality, this may be a good choice for analyzing and finding the hidden meaning in your data. In our next chapter on regression in Jamovi, we're going to look at associations, specifically through correlation and scatter plots. And we're also going to look at the ways we can use many variables to predict scores on one variable, how we can use predictor variables to look at an outcome or criterion variable. And we'll do this primarily through variations on regression. Jamovi gives us actually a great set of choices. We can do standard linear regression, one of the most powerful, flexible, and useful procedures available. We can also do binomial logistic regression, where the outcome variable is not a quantitative or a continuous score, but a dichotomy, this or that. And you're trying to use a collection of variables to predict which of two categories a case will go into. Then there's multinomial logistic regression, where you have several categories in your outcome variable. This is actually a very sophisticated procedure, and it's a surprising thing that Jamovi includes this, and it includes it for free. And then finally, we'll look at ordinal logistic regression, recently added to Jamovi, which allows you to use, again, a collection of variables to predict which of several ordered categories a case falls into. And between this set, linear regression, binomial, multinomial, and ordinal logistic regression, we have an extraordinary collection of tools for getting more insight out of our data. And in each case, what we are doing is we're using several variables to predict an outcome on one. I like to think of it as the statistical version of e pluribus unum, a motto of the United States, which means out of many, one. And in this case, out of many variables and many data points, one conclusion. And so let's look at the ways that Jamovi lets us use an entire collection of regression techniques to explore data and get useful insight out of it. Perhaps the simplest way of looking at the association between variables is with the correlation coefficient, specifically the Pearson product moment correlation coefficient, usually just called R. And it's a great way of looking at the association between two quantitative or continuous variables, although it's actually much more flexible than that. And I want to take a moment to show you how we can do correlations and correlation matrices and scatterplot matrices in Jamovi. Now, to do this, I'm bringing in a new data set, and it's called state data. And it's based on a little bit of information that I've compiled from different sources. One is the name of the state, its code, the region it's from. I looked up whether their current governor is Republican or Democrat. From a few years ago, a study done on categorizing states by their personality characteristics, putting them as temperamental or friendly and relaxed or traditional. Another study that classified these states by their big five personality characteristics, extroversion, agreeableness, conscientiousness, and so on. And then here at the end, I went to Google Correlate and I got state by state data on how common certain search terms are in each state. These are z-scores, so they tell you how many standard deviations above or below that state is from the national average. And I put in some that I felt were at least kind of relevant to the big five personality characteristics. I have some social media ones. I put in some businessy ones, entrepreneur. GDPR stands for the General Data Privacy Regulation that the European Union just put in. It's a big deal if you're in e-commerce. Then we have universities, and then mortgage, and then volunteering, and museums and scrapbook, and my favorite one, modern dance. And let's take a look at some of the associations between a few of these variables, and then we'll explore some of the other associations as we go through this chapter on regression in Jamovi. Okay, so the first thing I'm going to do is I'm going to pick a small number of variables. When you go to regression, your first choice here is correlation matrix. And, truthfully, you could put in 100 variables. You just end up with this absolutely gargantuan matrix and not be able to make sense of it. I'm going to be a little more selective and pick just a few right now. I'm going to pick one of our personality characteristics here, extroversion. So really how outgoing and social a person is versus being introverted. And I'm going to pick just a few other things to go with it. So maybe extroverted people might be on social media more. So we'll pick Facebook. And they may or may not be concerned about privacy. Let's see what that looks like. And then how about volunteering? So are they offering to do things for free to help people in their community. Okay, so I put those in there and you see that this table builds up and it fills in almost immediately. What we have are the correlation coefficients arranged in the top right diagonal of the table. There's nothing in the bottom left because those two are mirror images there, because the association between extroversion and Facebook is the same as the association between Facebook and extroversion. Down the diagonal are just these lines because that's each variable with itself, and that's always a perfect correlation, but it doesn't really mean anything. So what we have in this are two things. We first have the Pearson's R. This is the product moment correlation coefficient. It goes from -1, which indicates a perfect negative linear association, through 0, which indicates no linear relationship whatsoever, to +1, which indicates a perfect positive linear relationship. And we also have the p-value, which is used for the statistical hypothesis testing. And we're looking for a number there that is less than 0.05. Now, it's going to be easier to see what's going on if we come over here and click Flag Significant Correlations. It'll put asterisks next to them, which makes it a little easier to find instead of having to compare each number in your own head. And so we see, for instance, that we have 3 significant correlations out of 6. So it turns out extroversion is not associated with any of these things, which is kind of surprising. But states that search for Facebook more on Google search less for privacy. They also search less for volunteering. And then states that search more for privacy search more for volunteering. These are pretty good correlations. And again, it's on a state by state level. It's not a person by person level. It's on the states. By the way, the data set only includes 48 states. It doesn't include Alaska or Hawaii or the District of Columbia, Washington, D.C. That's because that's what was included in the one that categorized these states by personalities. And so this gives you something to look at. Now, one interesting option that Jamovi gives you is to do confidence intervals. And so we click on that, and it will expand this table and give us a 95% confidence interval. You can change it to something else if you want. And it'll give you the upper bound and the lower bound. So for instance, you can see that this one goes on either side of 0. So it's this and this. Here, however, this association between Facebook and volunteering as statewide search terms, we go from -0.451 to -0.789. So it may be that you want confidence intervals for your correlations. It makes for a busy matrix, but they're available. The other thing I want to mention is this. It's always nice to have a graph. And I actually would have called this a scatter plot matrix as opposed to a correlation matrix, but either one works. And what it is it's a similar rows and columns, but this time it has separate scatter plots for each of the associations. And they get kind of busy, but you can see that we've got a strong negative association, a strong positive association, and some others that are pretty close to 0. It's set up a little bit differently. Here we have stuff on the bottom left diagonal as opposed to the top right diagonal, but again, it's symmetrical. We can also get the density charts on the diagonal so we know what the distribution looks like for each variable. And from that, you can see that extroversion and Facebook are kind of normal. We got a peculiar shape here with privacy because we have outliers, and volunteering is bimodal. And then also we can get statistics. That'll give us the actual correlation coefficients displayed on the upper right side of the diagonal in the scatter plot matrix. See, these numbers correspond to what we have up here. There's the 0.036, and there's the same thing down here. And so we have both a numerical summary of the correlations, the associations between these variables, as well as a graphical summary. That's generally how you want to do it anyhow. And so correlations are a fabulous first step at looking at the association between variables, especially when they are quantitative or continuous variables. Again, it's more flexible than that, but that's the canonical usage of correlations in Jamovi and elsewhere. Sometimes you want to just do more with less. And if you want to be able to do as much as possible with the smallest number of tools as possible, then linear regression is going to be by far your best bet. It is the general purpose data analytic tool And so many of the other procedures that we look at are actually special versions or variations on linear regression. The basic idea here is you're trying to take one or more variables and use those to predict scores on a quantitative or continuous outcome variable. Let me show you how this works using the state data that I have. This again has information about whether the current governor is Republican or Democrat, some psychological information about states on the big 5 personality characteristics, and a bunch of Google search information that's given in z-scores. Let's try to predict one variable here in particular, and let's look at openness. That's an interesting one. It has to do with being open to new ideas, or sometimes with art, but mostly it's associated with being open to thinking about new things and trying new perspectives. It's a nice thing. So let's come up here to regression, and let's do linear regression. And what we're going to do is we're going to pick openness as our dependent variable. It isn't really a dependent variable because it's not from a manipulated experiment, but it's the outcome variable. And the idea here is that the outcome scores depend on the other variables we put into the model. So let's take openness. Now, I have a small data set. There's only 48 cases in this because it's the contiguous United States. And so I can't go hog wild and throw everything in there because I'm going to violate some of the assumptions of regression. So I'm going to be a little bit selective, just a little bit. Just not going to put everything in there. I'm going to pass up some of these other things. I'm going to leave these other big 5 personality characteristics right here because they're not supposed to be associated. But I am going to come and get these Google searches. And again, what it tells us is what is the state's average on this as a proportion of their total number of searches. And it's given as z-scores compared to the rest of the United States. So I'm going to select all of those and put them over here into covariates. And actually, I think I will take one of these categorical variables. I'll get governor. This is a dichotomous variable. In this particular data set, it only has 2 values, Democratic or Republican. There actually is an independent governor right now, but he's up in Alaska. And Alaska wasn't included in this data set because we don't have the psychological information for them. So we can treat it as a dichotomous. I'm going to put that here under factor. And you can see that off to the right, the regression table has filled in almost immediately. We can tell a couple of things here. First off, the multiple correlation, the big R here, is 0.831. Again, correlation goes from -1 to +1. And this is a strong correlation. With multiple regression, like we have right here, it's more common to look at the R squared, or actually the adjusted R squared. I'll show you in a minute. But this can be interpreted as the proportion of variance in the outcome, openness, that's predicted by these other variables. And it's 69%, which is truthfully is kind of huge. And if we want to, we can come down here and look at these individual variables and how they contribute. Now, keep in mind, these coefficients, these are the things that you multiply each number by, are only valid when you take this set of variables together. This is not how much is associated on its own. This is as a whole. So if I were to drop one of these variables out or add another one in, all these numbers would adjust a little bit because it's the unity here that's important. That said, we can tell that some of these seem to matter more than others. We're looking for p-values that are less than 0.05. And we're not getting much here on any of these until we get down here at the bottom. Scrapbook. This is how much does that state search for the term scrapbook compared to other states? And that makes a difference. States where scrapbooking is more common of a lower level of openness, at least when taken in the context of this entire set of data. And then searches for modern dance are in fact significantly associated with higher levels of openness. Again, within the context of this set of variables. And then down here, governor is a dichotomous variable that takes 2 values. And the nice thing about Jamovi is it's able to simply take a categorical variable and throw it in there and prepare it to work well in a regression. On the other hand, we see that this one's nowhere close to statistically significant, so we don't really need to worry about it. But let's come over here and see what some of the options are for linear regression in Jamovi. I'm going to scroll up here a little bit. Let's go to Model Builder, and this is if I wanted to put the information in blocks, that actually might be a good thing. In fact, let's try that. Let's do blocks where I'm going to take all of these variables out right here, and I'm going to make the first block just the governor, whether that person's Democrat or Republican. And then I will add a second block that takes all of this other information, and we'll just drag them over to right there. It should show up in a second. Dragging all of them at once. I'm going to try adding them one at a time here. I'm going to click Instagram and I'll drag that over right here. And what this is going to do is it first creates a model that has just the governor in it. And then it's going to see how much better the correlations get, the associations get, when we put in these other variables. I'm just dragging them over one at a time. It's going to take a moment to update everything here. Privacy and university and mortgage and volunteering and museum and scrapbook and modern dance. And so we'll see what those are able to add in addition. It's going to take a moment for it to update the results here. Comparison of two different models because I entered them in blocks. The first one has just the governor, and it actually is associated a little bit there. If we want to see the specific results, we can come here and click Model 1. And that shows us just the governor. And what's interesting is when we have only whether the governor of a state is Democratic or Republican, we actually get a strong association. And that reminds us that's very different from what we had when we entered everything at once. Now let's take a look at Model 2, which in addition to that adds the other variables. Now, by the way, when it's just the governor, you see we have an R squared of 0.148. That's not bad. When we throw in the other variables, it goes all the way up to 0.69. And that change from Model 1 to Model 2, where the R squared went up by 0.542, is statistically significant in and of its own. But let's look at Model 2 here again. And now we can see, again, the funny thing here is when we put in all these other variables, that the governor's Republican or Democrat doesn't matter anymore. Again, it's changed by the inclusion of these other variables. And this gets to the results that we had previously, where scrapbooking, they're in a different order because I dragged them in differently. Scrapbooking nearly significant, and modern dance is the only one that's significant on its own within this group. By the way, you may notice we have the option of entering variables in blocks. Block 1, block 2, block 3. That actually is a good way to go if you want to look at the separate or additional predictive ability of one variable or another. One thing you do not get to do in Jamovi, and some people say this is a very good thing, is you can't do stepwise variable selection. You can't throw a whole bunch of variables at it and say, look, you just sort through it all on your own and tell me what works. That's an easy way to do things, but it tends to really magnify the result of weird, fluky results in the data, and you tend to get results that don't generalize well. And so that's not even an option here. You can, however, do blocks where you choose what goes in at one point and you examine what's happening. I actually prefer blocked entry like this. For reference levels, that's for categorical or nominal variables, and you get to decide which category is the baseline one and which one gets the regression coefficient that goes with it. Right now, it's Democrat as the baseline, Republican goes on top. I can just flip it around, and then you can see that this will switch over here and it'll just change the sign associated with it. So it doesn't change anything big. While that's refreshing, I'll close this and come to assumption checks. There's a number of things that need to be true for the results of linear regression to be meaningful. Now, autocorrelation is if you had stuff like week 1, week 2, week 3, where the week 3 results you know are going to be at least partially associated with week 1. We're not dealing with that, but we are going to be dealing with collinearity, where the predictor variables are associated amongst themselves. And that's what causes the associations to change dramatically when variables are in different combinations. If no variable was associated with any other, it wouldn't matter the order that you put them in or whether they were in there with the others or not. It would always be consistent. But because these variables are associated, it becomes very sensitive to the way that you enter them. Let's scroll down a little bit and let's look at two collinearity statistics. The first is VIF, which stands for variance inflation factor. And the second is tolerance. And you can take the two of these as an indication of how associated each of these variables is with all of the others. Now, I can tell by looking at this that we do have some collinearity or multicollinearity, so interaction between them. It's not the end of the world. I'm going to go past it. We can also look at something like the QQ plot of residuals. That's the quantile plot of residuals. When you do a regression, the residual is the distance between the predicted values you give people and their actual values. It's the error, the leftover part. And in theory, that should be normally distributed. You shouldn't always be high or always be low. It should be spread out basically like a bell curve. And if our residuals were perfectly shaped like a bell curve, they'd all be exactly on this line, but you can see they're really close. So that part is nice. You can get separate residual plots. It'll do one for every one of the variables that you put in there. You can also get Cook's distance, which is a way of looking at how influential a single data point is. I'm going to skip over those and come down to model fit. We have R and R squared. And if I come back up here, you'll see where those things go. Adjusted R squared is probably going to be a better choice in this situation, especially because we have a small data set. There's only 48 cases. And you can see that there is a change. The R squared is 69 and the adjusted R squared is 572. This is going to be a more accurate number in terms of generalizing to other data sets. We have other information we could use like the AIC, that's the Akaike information criteria, or the Bayesian information criteria. We can also do the overall F-test. Let me click on that and you'll see how it expands some of the information that we have in here. What that does is it adds a few more columns here where we're doing the overall model. Now we have two different models, so we have two different entries. When it was just the governor, we had a highly significant result. And when we added on all the Google search information, we got an even stronger result here. In terms of model coefficients, one thing you can do is you can do the omnibus F-test. We've basically done that. But what I would like to do is get the standardized estimate. So instead of t-tests here, we'll actually get z-scores where we can compare the regression coefficients against each other. And we can even get a confidence interval, 95% confidence interval for those. Over just a little bit. And the standardized estimate, these are z-scores for each of these variables over here as opposed to t's. And then we have confidence intervals for each of them. And you can see, for instance, that we have one here that is going to be the modern dance one, where the two sides of the confidence interval have the same sign. They're both positive, which corresponds with it being statistically significant. And then finally, you can get estimated marginal means. So for instance, we can come down here and we can put governor into one of these. We can put it right there. And that will produce a new chart down here at the bottom. And while that's working on it, I'm going to add another new term. Let's say, for instance, let's put modern dance in there. And you can do this for each of them if you want. What this is showing us is the level of openness for the state broken down by whether that state currently has a Republican or Democrat governor. And you can see that there's an enormous amount of overlap between those two. And then this is the more fun one. It's when you take something that is measured on a quantitative scale, you get sort of this regression line in terms of how open people are. And this is the standard error estimate or confidence interval for the regression line. And so you can see that as modern dance becomes more common as a search term, that the level of openness for the state goes up as well. And again, you can do that for every one of these other variables. It's just going to be an enormous amount. But the general idea here is that this is the set of tools that Jamovi gives you for doing linear regression, which is probably the single most important analytical procedure you can have when you're working with your data. In the first video on linear regression, I showed you how to set up the most basic version of linear regression, which is called simultaneous entry, where you take all of your predictors and you put them in the model at once. And what it gives you is this one that we have right here, which gives you the t values and the p values that allow you to do hypothesis tests on all of your variables, but only in the context of each other. And if you select different variables, or sometimes if you put them in different order, you can get different results. Now, I want to show you some of the options that Jamovi gives you for this. And to do that, I'm going to come back to regression, and I'm going to pick linear regression again, and I'm going to set up a new analysis. I'm going to scroll down a little bit here. The outcome variable, the dependent, is openness. So I'm going to pick that right here. And this is where I can start choosing which variables I want to include in the analysis. Now, what I did previously is I picked all of these Instagram down through Modern Dance, which are Google Correlate terms, which have to do with the relative popularity of these search terms on a state-by-state basis. And I can pick those, and I also chose governor, which is simply whether the governor of that state was Democratic or Republican when the data was gathered. And we have this table right here, but what I'm going to do is I'm going to come down here to Model Builder. And here I have an opportunity to do data in blocks. Now, a very common approach, or something that a lot of people want to do, is something called stepwise entry, which you simply tell the computer, these are all the possible variables, and I want you, the computer, to go through and pick the one that has the highest individual correlation, stick that in the model, then pick the one that has the highest correlation after that and put it in, and so on and so forth. The problem is stepwise models tend to really build on the idiosyncrasies of that particular data set. And so you get a model that's really well tailored to what you have, but it doesn't generalize well, and it can actually mislead you in a lot of different ways. Jamovi doesn't even give you the option for that. What you do have the option for is what I personally call block regression, or block entry, or block-wise regression. And that is, you can set up several models that sequentially add additional variables. And so what I'm going to do here is I'm going to first take all of these search terms. I'm going to get all of them out. And so right now, block one is just whether the state has a Democratic or Republican governor. And you can see right here that in terms of openness, it's doing subtraction, Republican minus Democrat. And what that means is that the Democrat governors, or the states with Democrat governors, tend to have higher levels of openness than the ones with Republican governors. That's because we have a negative coefficient there. But let's add a second block and see how things shift around. Now, I do want to come up here and change this to include the adjusted R squared. So I'm going to come down and say model fit and add that on right there. And I'll close that. So now we have our model fit. Simply knowing whether a state has a Republican or Democrat governor predicts almost 13% of the variance in the outcome, the openness of the state as a whole. That's kind of remarkable all on its own. But I'm going to come over here and add a new block. And in block 2, we're going to try to put several other variables. We'll say, for instance, come down and pick just these last few: museum, scrapbook, and modern dance. And I'm going to put those into block 2, just as a main effect right there. And then I can compare the model with just governor and then the model with governor and these three in it. And so that's what I have right here. We have this first one is just governor, and we have an adjusted R squared of 12.9. It explains about 13% of the variance in the outcome openness. When we add these other three Google search terms, the relative popularity of those on a state-by-state basis, it goes up to 52%. We've now explained over 50% of the variance in the outcome, which is openness. Now, that makes a little bit of sense because openness often includes artistic or creative openness, though it can include a lot of other things as well. And this one right here, this model comparisons tells us that there is a statistically significant increase, which makes sense because it's a huge jump. And then here we have the variables. Now, this is for model 2. If we want to look at model 1, we just click on this and we get the one with just governor. And you can see there's a statistically significant effect there. That's the 0.0007 right here. But let's go back to model 2. And now we can see that governor is no longer statistically significant. That's because it was a spurious correlation. It's predicted by other things. And then museum doesn't seem to matter, but we have strong and statistically significant effects for both scrapbook and modern dance, two creative interests. And we see that one's negative and one's positive. So in the states that have higher levels of interest in scrapbook as a search term, there are lower levels of openness. And in states that have higher interest in modern dance, there are higher levels of openness. Again, that's because we have these negative and positive coefficients. But remember, it's always within the context of one another. Now, if we want to, we can add a third block where we take on, for instance, these other ones. We go from Instagram, and then I'll do a shift click down to volunteering. And I'll put those in the third block as main effects only. We're not looking for interactions right now. And when I do that, we can see that adding those variables improve the adjusted R squared from only 0.525, that's 52.5%, to 57.2%. And in fact, you can see here that that increase from Model 2 to Model 3 is not statistically significant. The increase has a p-value itself of 0.180. So we didn't get anything helpful by adding those extra variables. In fact, we lost degrees of freedom by doing that. So that tells us that we're probably best off going with Model 2, which had a substantially higher rate of predictive ability compared to the one that had just governor. And the results make sense, and it's that theoretical interpretation that matters. And so this is one way of looking at the relative contribution of different variables. Now this one's theory driven because you decide what the blocks are and you enter them in and you interpret the results on your own to see if they make sense and how applicable they are, and really whether it's something that you can put into use, whether you can do something productive with it. That is the goal of linear regression and this blocked entry, is to find the information that's going to be most useful to you in solving the problems that you're dealing with. Before you take the results of your linear regression and you go running off to market and making massive changes, you do want to make sure that you actually dotted your I's and crossed your T's, and you want to make sure that your data met the assumptions that the model has and that your data is leading you in the right direction. This becomes a matter of checking what are called regression diagnostics, a number of statistical and graphical methods for looking at how well your data fits the model. Now, I'm going to do this by coming back to the same model and data that we used before, where we're looking at variables to predict the openness of people on a state-by-state basis. And I'm going to click on this model right here. And what I'm going to do is I'm going to come back not to Model Builder, although that is where I specified the blocks that I was going to use, but I'm going to come down a little further to Assumption Checks. And this is where the most important things are going to happen. Now, there are a few here that are particularly important. If you have data that's measured repeatedly over time, like Q1, Q2, Q3 results, then you're going to need to deal with autocorrelation to see how much a carryover effect there is from one time to another. We don't have that right here, so I'm not going to deal with that. But we do need to be worried about collinearity or multicollinearity. And that's what happens when your variables that you're using to predict the outcome are correlated with each other. Now, really, the easiest way to check that is to get a correlation coefficient and look at the associations between your various predictor variables. But the statistics that are specific to collinearity within linear regression also tell you important things. We come down here, it's giving us two measures in particular, and we're looking at Model 2, that's the one I have selected. The first is VIF, which stands for the Variance Inflation Factor, and the second one is tolerance. And there's a correlation or an association between those, and what they're both referring to in different ways is the association of each of these variables with the other predictors in the model. And I can tell by looking at these that we do have some crossover between them. The actual ways that they operate gets a little complicated, and that's beyond what I'm trying to do here. Mostly I want you to know that Jamovi is able to do this for you, and you can interpret the results in ways that are going to make your model more robust. You can also do the QQ plot of residuals. I've demonstrated that elsewhere, and it's relevant here too. The residuals, or the leftovers from predictions based on your model, need to be approximately normally distributed, and they need to not flare out on one end of the model or the other. Now, I do see that there's one down here dipping kind of low. The rest are basically on the line, and we come off a little bit. It's not horrible, though you may want to do a little more of a drill down analysis to see what's happening in this particular data set. There are two ways you can do that. One is with the residual plots, and that's going to do separate plots for each of the predictor variables that we have in the model. And so it's going to take a moment to catch up with all of those. And the other one is what's called Cook's distance, and that's going to give you a measure of the influence of specific cases. Now, because we have only 48 cases in our data, it's the 48 continental United States, that's not such a horrible idea. And here we have the plots that we're looking at. We see, for instance, with openness, there's this pattern in the residuals that we don't have in other things. And so that's an issue we may be concerned about. I'll click on Cook's distance as well. And Cook's distance actually shows up above the charts that we have right here, and is simply giving us the mean, the median, standard deviation, and the range of these. And so you can look at the individual scores that you have and try to find out what's going on in the residuals plots to see if there's something that is deviating really sharply from your expectations or the assumptions of the modeling technique. I do want to finish with one other thing, and that is the estimated marginal means. Now, this will be more helpful in some situations than in others, but what you can do here is you can actually try to get a chart that shows you how these variables predict your outcome. So I can take governor, which is an easy one because there's only two categories there, and that's going to make a chart. It'll be down here at the bottom. This simply gives me the mean level of openness for the states with Democrat governors and the mean level of openness for states with Republican governors. And you can actually see, well, the means are a little different. This dot is a little lower than this dot. The confidence intervals overlap substantially. And you can do this with other terms if you want. We can take, for instance, modern dance here, and we can put that in. And it's going to be a little different because this is a quantitative or continuous predictor, whereas the governor was a dichotomous nominal variable. And we'll scroll down a little bit. And what it is kind of like a scatter plot, but there's no data points on here. And instead, we're looking at a regression line with a confidence interval around it at the association between the two as how modern dance predicts the expected levels of openness. And you see as the relative interest in modern dance goes up to about a level of 4 point something, that the average level of openness for the states goes up as well. And so this can be a way of also seeing how well your data match the assumptions and fit in with the approach of linear regression, which after all is one of the most common and most powerful methods of using data to model specific outcomes, and something that Jamovia makes incredibly easy to do and to interpret. One really common task in analyzing data is classifying cases into one category or another based on a number of other variables you might have. So for instance, with your computer, it's trying to decide whether a particular email is spam or not. We're trying to decide whether a particular person is likely to buy your product or not. And those are dichotomous classifications. And a common method for analyzing or predicting dichotomous outcomes is to use what's called binomial, which means two names, binomial logistic regression. So it's a form of linear regression, but it's adapted for placing cases into one group or another based on the probabilities that are predicted from your other variables. Now, this is really easiest to simply show how it works. So I'm going to use the data I have about state data. I've got a number of variables about personality characteristics on a statewide basis and search terms. But the dichotomous variable that I have in here is whether the state's governor, their current governor right now, is Republican or Democrat. Now, let's start with just a little tiny bit of exploration so we know what we're dealing with. I'm going to take governor, put it over here, and we're going to get a frequency table, and we will also get a bar plot. And so at this exact moment of the lower 48 states in the United States, about 2/3 of them have Republican governors. And so we're going to see if we can use some of the other data we have in this data set to classify states or predict which ones have Republican governors and which ones have Democrat governors. And so the way we want to do this, I'll just close that, is to come to regression and come down here to logistic regression, two outcomes, or binomial. Again, where binomial means two names or two categories. I'll click on that. The first thing we need to do is put our dependent variable, that's the outcome variable, the thing we're trying to predict, and that's going to be governor. And I don't even have to tell it, this is what this means, this is what that means, because I actually have it written as words in the data set. And the nice thing is Jamovi is smart enough to be able to tell that those are categories. And then we get to pick some covariates. Now I could pick a lot here. Let's pick just the social media ones, just for fun. So I'm going to come down here to Instagram, Facebook, and retweet. By the way, the reason it says retweet is because Google Correlate wouldn't let me search for Twitter. I don't know why, but since retweet is exclusively a Twitter word, it seemed like a good substitute. So I'm going to put those all into covariates. And those are the three variables that I'm going to use together to try to predict which states have Democrat governors and which states have Republican governors. And you can see right here, we've got a model that's actually working pretty well. We've got three variables. We have the intercept, which is not 0. Instagram is not statistically significant. Facebook is, and retweets nowhere close. But there's a lot of other information we can get through the options that we have in Jamovi. So let's just take a quick look. Let's take a look at Model Builder. And this is how we want to enter things, and we can put stuff in blocks if we want to. I don't feel the need to do that in this case, but I showed how that works in the video on linear regression. Let's look at reference levels. And one of the categories needs to be taken as the baseline, and we're trying to predict a change to the other category. Because there are more Republican governors, let's just have Democrat as the baseline, and we'll go up from there. Assumption checks. Collinearity is an issue, especially because I'm pretty sure that these three social media terms as Google search terms are related. And from that, we get both the VIF, the variance inflation factor, and the tolerance. And there's indications here that we've got some collinearity, but nothing awful. We have a few choices on how we assess fit. I'm going to leave this with the defaults, where it uses deviance in the AIC, which is the Akaike Information Criterion. Then we go to the model coefficients, and a common choice when you're dealing with binomial logistic regression is the odds ratio. And it's also nice to get a confidence interval. And that's going to add a few columns onto this table right here. You see, we've got the odds ratio right there. Now, in so many other statistics, 0 is the base value, and things either go positive or negative. But the nothing's happening value for an odds ratio is 1. That means a 1-to-1 ratio. And it goes below 1, but it doesn't go all the way down to 0. It can't get all the way down there. And it can go up from there. And so you see, for instance, that the intercept is reliably above 0, but you can see that its odds ratio, both of these numbers are above 1. This one, 1's below 1, 1's up. These, both of them are above 1. They're on the same side. And so these give us an idea of the variables that predict the odds of a particular state having a Republican governor based on these three social media variables that we have from Google Correlate. If we come down a little further, we can go to estimated marginal means. And so, for instance, Facebook was significant within the context of these three predictor variables. Let's take that and stick it into here for marginal means, and it actually gets a nice curved chart that goes with it. If I come down here for a moment. And what this shows us is the probability of a state having a Republican governor going from 0 to 1. That's like 0% to 100%. Based on the z-score that state has on searches for Facebook on Google. And you can see here that when states search less than other states for Facebook, they are less likely to have a Republican governor. but when they search more, they are more likely to have Republican governor. And so this is a nice way of looking at the effect of that, because binary logistic regression does work on a curved system where it's drawing this probability changing over time. This one shows you just the one variable. It actually uses all of the variables together to calculate probabilities. But another nice thing about categorization tasks like this is you can get a classification table. So I can click on that one right here. And what it's going to tell me is what it predicts states will have versus what they actually do. And what's interesting too is you can change the cutoff value. So for right now, it's only getting 40% of the Democrat states correct. It's getting 91% of the Republican ones. But let's take a quick look at what's called a cutoff plot, which gives us a chart of what's called specificity and sensitivity. You can think of sensitivity meaning like it's very likely to set off an alarm or to give you the answer if it believes it has a Republican governor. And specificity means it's going to do that only if it does. And in many situations, these two lines, this is specificity going up here, and this is sensitivity going down. Often they cross right here at the 50% point, but these ones are a lot closer to 0.7. So what I'm actually going to do is I'm going to change the cutoff from 0.5 to 0.7. And do that right here. And you'll see that it changes the way the classification table works, because now it's going to say, well, only put them as Republican if they have over a 70% chance of being Republican. And that actually makes sense too, because it's about 2/3 Republican governors, slightly over, in the country as a whole. You see this cutoff line is a lot closer to where these two crossovers, usually where you want to get. It's because it's going to be maximum utility there. And it's changed the classification table. Instead of 40%, we now have 73% correct for the Democratic governors. And we've gone from 91 to 73, but now it's sort of balanced out in terms of how accurate it is for the two different conditions. And so these are some of the methods that Jamovi gives you for looking at the relationship between several predictor variables, like the 3 social media search terms, and how they can be used to predict the classification of a dichotomous outcome like Republican or Democrat governor, or any other time you have two distinct outcomes that you're trying to predict. We're at a point where things are going to get very complicated. At least they could get very complicated. Multinomial logistic regression is potentially a very sophisticated analysis. What you're trying to do is use several predictor variables in a regression equation to predict not two categories, but several categories. And although it may not sound like a big change, the processing behind it becomes exponentially more complicated. Fortunately, Jamovi makes it possible to do a relatively simple multinomial logistic regression. I'm going to demonstrate this with the state data, and I'm going to look at this one category here, which actually has to do with psychology profiles for the various states in the United States. Let's start by doing this. Let's do a quick exploration and get descriptives for psych regions. I'm going to put that over here. And I want to get the frequency table, and I want to get the bar plot. And this is based on an analysis of people's online behavior and other characteristics. And the researchers ended up with 3 categories, what they called friendly and conventional, which is half the states in the sample, relaxed and creative, that's 10 states, or about 21%, and temperamental and uninhibited, that's 14 of the states in this sample. And here's a bar chart. You can see them, and unfortunately, the labels don't automatically adjust in Jamovi at this point, but that'll happen eventually. But let's see how we can use other variables to predict which states go into which categories. And what I'm going to do for that is I'm going to come back up here to regression and go to N outcomes. That's multinomial logistic regression. And when I click on that, the first thing I have to do is pick what my dependent variable is. What's the thing that I'm trying to predict? In this case, it's the psych regions. So I'm going to put that right there. Now I've chosen one with just 3 categories. That's going to be the simplest. If we had only 2, we'd do binomial. And if we had more than that, it just gets so complicated, it's hard to deal with. In terms of covariates, what I'm going to do is I'm going to pick the 5 elements of the big 5 personality factors. So that's extroversion, agreeableness, conscientiousness, neuroticism, and openness. Mind you, this is not on a person by person level, it's a state by state level. I'm going to slide that over into covariates. And then from there, we can start looking at the model that it creates. It takes a moment sometimes for it to run through this because there's a lot of calculating that goes on behind it. Let me close this so I can slide this over for a second. We have a pretty big table here. The first one is the fit measures. So we have deviance, we have the AIC, and you'll see that a lot of this is very similar to what we had in the binomial logistic regression. We also have the model coefficients where it's comparing the different groups, the relaxed and creative minus the friendly and conventional. And it's looking at these various elements, the personality factors. And we have the p-values over here. And we see that, for instance, when distinguishing between relaxed and creative, none of these seem to make a big difference. When we look at temperamental and uninhibited versus friendly and conventional, we do get one. Conscientiousness appears to be an important one, and neuroticism is nearly there. Now, let's take a look at some of the options we have. Click back on this. And I come down to Model Builder. I can put the variables in blocks if I want, and there may be situations where there may be situations in which I want to do that, but with just these 5 personality ones, I'm not going to do blocks. But I did demonstrate that in linear regression, so you could take a look at that. Reference level is what's the one I want to compare it all to. I actually think I'm going to take the temperamental and uninhibited and make that the reference level. And you can see how the order just switches around over here. So this is friendly and conventional minus temperamental and uninhibited. And it just changes the sign of some of the comparisons. Although you see down here, neuroticism becomes an extremely big thing for distinguishing between the relaxed and creative and the temperamental and uninhibited. We're going to follow up with that. We'll come down to model fit. These are the standard choices here. We'll keep those as they are. And model coefficients. Now, this is where we have the estimates. Those are coefficients, but it's nice to have odds ratios and confidence intervals for those as well. And when I do that, I just get a few more columns over here. Now, you can ignore this one because it's for the intercept. We don't expect anything particular there. It's the rest of the ones that we're interested in. And you can see, for instance, here, this second to bottom one, this is relaxed and creative minus temperamental and uninhibited. We're looking at neuroticism, which has to do with kind of having a lot of mood swings or also getting irritable. And we have a significant association here. The odds ratio of 0.731. Remember, the null value for an odds ratio is 1. If it's either below 1 or above 1, then you have something going on. And especially if both sides of the confidence interval are on the same side of 1, as we see here. But this is all going to be a lot easier to interpret if we get the graphs. And so I'm going to come down here to the estimated marginal means. And now it's going to take a moment because I'm going to put all of them in here and I have to do them one at a time. I'm going to take extroversion, put that over here. I'll add a new term, do agreeableness. Add a new term, do conscientiousness. Add a new term, do neuroticism. And add a new term and do openness. And then I'm going to close this for right now. And what we're waiting for are all the graphs that are come at the bottom. Really pretty graphs. What they are lines that show the probability. So we have our 3 regions, each of which is shown by a different color. So this gray line right here is the friendly and conventional. And by the way, this shows us extroversion, where the mean is about 50 and it goes down to about 30 up to 70. And so as extroversion goes up, there's a much higher probability that that state is in the friendly and conventional. You can see that when extroversion is low, it's probably relaxed and creative. And the temperamental and uninhibited is just kind of low all the way through on that one. Agreeableness, friendly and conventional, is really high all the way through. You can see that the temperamental and uninhibited, low agreeableness, so they're a little cranky there. as it comes down, it becomes less likely that they are one of the temperamental and uninhibited because they're more agreeable. Conscientiousness has this amazing crossover where friendly and conventional, as conscientiousness increases, friendly and conventional, the probability of a state being friendly and conventional increases dramatically. And we have the exact opposite for temperamental and uninhibited, much lower levels of conscientiousness. And it doesn't seem to really figure into the relaxing creative states. And then neuroticism with this really peculiar, huge crossover. This is temperamental and uninhibited as neuroticism levels get higher, relaxed gets low, and then we have a funny little peak here for friendly and conventional. And then openness, we see that the friendly and conventional, as openness increases, they start out on the low end and then it drops off and the other two pick up. So there's a trade-off there. And so this is a really neat way of seeing a visualization of the probabilities and how each factor goes into determining whether a state falls into one of these three different categories. And this is probably how you're going to get the most information and the most insight into your data is through these marginal mean graphs, but you also get an idea for which ones really matter overall by looking at the calculations and the numerical summaries in the multinomial logistic regression. One final variation of regression that we can get in Jamovi that really is kind of surprising considering it's not always available in other programs is ordinal regression, or specifically ordinal logistic regression. And the idea here is you're trying to take several variables to predict where a particular case falls in ordered categories, say for instance from lowest to middle to highest. Now, you could theoretically have an entire ordinal scale where you rank every case from 1 to however many there are. But when you have a small number of cases, this is where ordinal logistic regression is going to be most useful. And another time that it shows up is really handy is when you have data that really deviates from normality. Now, I'm going to use this example data of state data that I uploaded. And we have, among other things, how much different states search for different things. And one that's kind of interesting here at the very end is searching for modern dance. Now, let me show you what this looks like because then you'll understand why the procedure is necessary. If we put modern dance right here, it'll give us some statistics, but what we're really interested in here is the plot, the density histogram. So we have data from 48 contiguous states, and you can see it's mostly normal, but man, we got this big gap and this bump up here. I happen to know that this is Utah, where I live. Utah, it turns out, leads the national mind share for modern dance, which is kind of shocking. Anyhow, this is not a normal distribution, and outliers like this can really cause problems with regular analyses. And so redoing the data, transforming it, and possibly putting it into categories might be one method of dealing with this, and ordinal logistic regression makes that possible. Now, what I want to do to make that happen is I want to split it up into categories. So for instance, let me come back to this just for a moment where I was. And let's go to statistics and say, what are the cut points to create 4 equal sized groups? So we're going to make quartiles. And what this says is, well, the minimum z-score is minus 1.44. The 25th percentile, the first quartile, is negative 0.618. The 50th is at about negative 0.23. And the 75th is positive 0.45. And it goes up to 4.7, I think. That's where Utah is, way up here. Now, I'm going to round these off a little bit. And what I did is I came in here and I created this new variable. I'm calling it modern dance quartiles. And what I'm saying is if the z-score is less than negative 5, put it in 1. That is, put it in the first quartile. If modern dance is less than 0, but above negative 0.5, put in the second quartile. If modern dance is less than positive 0.5, put in the third quartile. And otherwise, put it in the fourth quartile. And so that's a way of nesting if statements to create these categories. And when I do that, I can come back and do exploration again. except this time we'll do it for the quartiles. I'll put modern dance quartiles right there. We'll get a frequency table, and then we'll get a bar plot. And then you'll be able to see that it's a little better behaved because we've brought in the outliers and we've created 4 groups that are approximately equal size. They're pretty close. And the reason they're not exactly the same is because I intentionally chose to make the cutoff points something that seemed a little more sensible. But now we have an ordinal variable. We have the states categorized into the lowest quarter, the second lowest, the second highest, and the highest quartile in terms of their relative search preference for modern dance. And so I'm going to come here to regression and come to this last option here, ordinal outcomes. And when I open that up, the first thing I need to do is specify the dependent variable or the outcome that we're looking at, and that's going to be modern dance quartiles. I'm going to come back up here. I got it selected. I'll just click it over here. And then we put in covariates. We can put in a lot of variables if we want, but because I have a small sample size, only 48 cases, I'm going to limit it. Now, modern dance, because it's an art form, should be most associated with openness, because in certain studies on Big 5 personality characteristics, openness seemed to also have something to do with art. So I'm going to click that and put it over here in covariates. And then also, I'm going to show you how to use a factor. I'm going to take the psych regions, because that included friendly and conventional, but also relaxed and creative, which seems like it would be important for something like performing arts. And so if we take those, we have this table right here. It lets us know about the deviance and the AIC, which are methods of assessing the fit of the overall model. We have these predictors. Openness, it turns out, is significantly associated with modern dance quartiles. So that's something that we were kind of hoping for, that openness or being open to new ideas and possibly to aesthetic experiences seems to be associated with the number of searches, relatively speaking, that a state does for modern dance. We also see that the psych regions matter, that the relaxed and creative and the friendly and conventional, it makes a difference. And what's interesting, actually, in both cases, is that relaxed and creative does more than friendly and conventional does. That's because this is positive. And also temperamental and uninhibited does more than friendly and conventional does in both cases. So let's take a look at some of the options. We have the model builder. If I wanted to put things in separate blocks, I could. The reference levels. Let's go to model fit. This is where we have the choices. The deviance, the AIC, and the McFadden's R-squared all seem like great ideas, so I'm going to leave those. And the model coefficients. That's this table we have right here. I'm just going to throw one more thing onto it. I'm going to do the odds ratios and the confidence intervals for the odds ratios. Remember, the null value for the odds ratio is 1. And so if we are consistently below 1 in the confidence interval or above, that lets us know that we have something important here. And for instance, let me close this so we can see more of this output here. I'll drag this over. So openness, the odds ratio on both ends of the confidence interval are above 1. So, it's significant. But really, the amazing one is this here. Temperamental and uninhibited states versus friendly and conventional states. The odds ratio is 17.54. That's really big. And the confidence interval goes all the way up to 91. And so this is a very influential difference in trying to predict what a state's ranked category would be in terms of the quartiles 1 through 4 and their searches for modern dance on Google. And so it turns out that this is actually a really easy analysis to set up. We could theoretically have a lot more options available to us, but Jamovi's keeping it pretty simple. And this is a good way to get started in dealing with ranked information as opposed to the outliers that we had in the original distribution, and using a regression model with both a quantitative or continuous predictor variable and a categorical predictor to try to find out where states would fall into that ranked continuum that we created. In this section on analyzing frequencies in Jamovi, we get a new way to deal with data. Specifically, we are now dealing with counting as opposed to measuring. Now, measuring means when you say how long does it take to do something or what's the average score here. Counting is like counting the number of rocks, where you're able to enumerate the cases and put the frequencies in as your data. And this requires a different approach. In Jamovi, we have several options for analyzing frequencies. The first and simplest is what's called the binomial test. Binomial means two names, and is for when you have two categories of outcomes, like flipping a coin and getting the number of heads and the number of tails. If you have more than two outcomes, say for instance, you have baskets of several different kinds of mushrooms, you can use the chi-squared goodness of fit test to see how things are distributed across those multiple categories. If you want to look at two categories at once and look at the association, and say for instance, you want to look at something like the number of World Cup teams from different countries and break it down by male or female, because we know that in soccer, the American women have done fabulously well. The American men didn't qualify for the World Cup most recently. That's looking at an association between two categories, and you can analyze that with what's called the chi-squared test of association. You also have something called McNemar's test. This is a relatively unusual one. It's for looking at tables where you have related data, paired observations like data from twins, because they go together and you have to take together that consideration. Also, if you did the same person at time 1 and time 2, then the frequencies have this built-in association and you need to compensate for that. McNemar's test lets you do that. And then finally, there's also log linear regression. It accomplishes a lot of the same things, but it uses a different mathematical approach. It's based on regression. There's some pretty serious equations that go into it, but it is often a very flexible and very powerful technique for modeling the number of cases, the observations or frequencies within different cells of your data. And so taken together, this gives us a great range of options for a data analysis for counting and frequencies in Jamovi. Probably the simplest data situation is trying to analyze just two possible outcomes. You can call that dichotomous data because it's split into two pieces. You can also call it binary. And in this case, we're going to look at the binomial test, which literally means two names. Think of it as heads or tails, on or off, yes or no. And in this example, I'm going to use the state data, and I'm simply going to look at governor because that's the only binary variable I have in here. And let's do this first. Before we do a binomial test, let's get a little bit of descriptive statistics. I'm going to come over to exploration and go to descriptives. And all I need to do is get governor, put it over here into variables. It's going to tell me some things I don't really need to know. I might as well remove the statistics that really only work for quantitative or continuous variables. But what I do want is a frequency table, and what I do want is a bar plot. And when I get the two of those, it tells me what percentage I'm dealing with in terms of governors from state to state. We have 48 states represented, because remember, this data only is for the lower 48 states of the United States. And we have 15 Democrat governors as of about a week ago, and 33 Republicans. And here's a bar chart that shows the difference. And so that's really easy to see. It's about 2 to 1. Now, in terms of binomial test, what we're doing is trying to tell whether our observed proportions differ significantly from some particular value. In a lot of inferential tests, it's really obvious that the null value is 0. Well, in the binomial test, you have a few choices. Now, let me close this and come over to frequencies. And the first thing we're going to look at is the two outcomes or binomial test. It's under one sample proportion tests. If I click on that, it's actually a really simple dialog box. All I need to do is pick the variable that I want. I'm going to use governor and move it over into this box. You can tell it's looking for something that is coded in Jamovi as either a nominal, that is a categorical variable, or ordinal. And right now it's already done the test, and it has told me that these proportions are both significantly different from a null value of 50%. And I can get a confidence interval, which actually is a really nice idea in this particular case. And this lets me know that the percentage of Democrat governors has a 95% confidence interval that goes from 18.7% to 46.3%. And we have the flip side of that for the Republican governors. Now I'm going to close this for just a second so I can open it up again. This one is done with a null value of 0.5 or 50% each. And maybe that's not the value that we want to use. Right now we have 68.8% Republican governors. Let's say we want to compare it to maybe 10 years ago. And I don't know what the proportion of Republican and Democrat governors in the 48 contiguous states was 10 years ago. But let's just say, for instance, I'm going to do the confidence interval here. Let's say it was 60%. And we want to know whether there's been a change in the last 10 years. Then I can do this. And now it's going to compare these two numbers to 60%. And what we see here is it's a little different. Let me close this so we can see this. In the first case, because we're comparing to this 50% and each of these two values, because they have to add up to 100%, are equidistant from 50%, the p-value is the same for the both of them. On the other hand, when we move the null value away from 50%, in this case to 0.6 or 60%, then the p-values are very different. We find that the current observed proportion of Republican governors, which is 0.688, which is the same as 68.8%, that does not differ significantly from 60%. On the other hand, the number of Democrats does. And so we have this big difference depending on how you set the null value. And it's going to depend what value you use. If it's something that really should be just as likely yes as no, then the default value of 0.5 is good. But if you're looking, for instance, at a game that has 4 players, then the default value of any one player winning is 0.25. And there can be other values depending on what you think is most likely to happen at random. But no matter how you do it, the proportion test is a very easy test to do in Jamovi. And it gives you the simplest kind of data, just a simple yes-no outcome. And it does both an inferential test with a probability value and a confidence interval. When you're looking at the number of cases in either of two categories, you can do the binomial test, a very simple test, and we've showed that elsewhere. But when you have more than two categories, but still in a single variable or factor, then you get to do the chi-squared goodness of fit test. And it's kind of a silly long name, but it's the test you use for comparing multiple categories in the same variable. Let me give you an easy demonstration of this using the state data that you can download from datalab.cc. In this example, I'm going to use this variable that's called psych regions. It's based on psychological research that builds profiles for states in the United States. And we're going to start with an exploration where we get basic descriptives of this. All I'm going to do is pick psych regions, move it over to variables, and I'm going to change the statistics. We don't need these ones because those are for quantitative or continuous variables. There we go. I'm going to get the frequency table, and I'm going to get a bar plot. It's really simple stuff. Now, of the 48 contiguous states that the researchers looked at, they classified 24 of them, that's exactly half, as friendly and conventional. That's our biggest bar right here. I'm sorry that the labels are overlapping. I'm sure that'll be fixed in a later release of Jamovi. The next category is relaxed and creative, which includes 10 of the 48 states. That's about 21%. And the last category is temperamental and uninhibited. That's 14 of the 48 states, or about 29%. And so we can look and see, for example, whether the states are evenly distributed across these three categories. Now, we can tell by looking at the bars that obviously they're not all the same. The question is whether that difference is statistically significant. And that's where we do the chi-squared goodness of fit test. Now, there's an important choice we get to make, and that's how we define our null values. By default, it's going to assume equal frequencies or equal proportions in each category. So let's come to frequencies here and go to n outcomes. That means more than 2 outcomes, an arbitrary number. And that right there is chi-squared. It looks like an X. It's actually a capital Greek C. It's called chi. Chi-squared goodness of fit. So we're going to click on that one. And all we need to do is take our variable here, psych regions, and put it right here in the variables. Now, this option for counts is when you have a summary table in your data set. And I'll show you that in a later video, how that can work. But because we have a raw data where everything is listed as one row per case, which is most common, that's the kind we're going to use right here. And what we have over here is a proportions test where it says that a proportion of 0.5, that's 50%, or in this one, 28,292. And it tells us that the chi-squared goodness of fit gives an inferential value where the calculated value of chi-squared is 6.5. 2 degrees of freedom gives us a p-value of 0.039. The standard value of p, or probability, that we use for significance testing is 0.05. So this would be a statistically significant finding. But I want to show you two other things we can do. One is exactly what is the algorithm comparing these values against? Well, it's comparing them against expected counts. And the way it does expected counts is right now, it just takes however many values you have and it splits them evenly across the number of categories. Well, 48 states can be divided evenly into 3 categories by having 16 each. And what the chi-square does is it looks at the deviation between 24 and 16, 10, 16, and 14 and 16. Does some manipulation on those, and that's where the value of chi-squared comes from. And so if we are looking for exactly the same number of states in each category, we have a result that is significantly different from that. But let me close this and do another analysis where we're not looking at strict equality across the 3. There are lots of times where you expect a different number of people to be in each category. So for example, if you're looking at the number of left-handed and right-handed people, well, there's more right-handed people overall. You don't expect it to be split totally evenly. So there is another way you can specify values other than strict equality. Let me put psych regions back in here, and we'll still get expected counts. But now I'm going to click on this menu to get expected proportions. And what I can do here is, you see, it's saying that by default, it's going to split it up across the 3. So 33.3% in each. I can put it as a different value. And you put in the ratios here, and that means like 2 to 1 or 3 to 1. If you want to, you can enter them as percentages. So you can say like, oh, let's have 60 here, and let's do 25 here, and let's do 15% here. And that gives us the values that we would expect in each of these conditions. I think that adds up to 100. And now what you see is our values, we have different expected values. And now we still have a statistically significant result. But I was able to specify different values. And you can see how up here, the expected values are 16, and it's the same in each case. Here, the expected values change from one to the other according to the values that I gave it. It's still a statistically significant result. In fact, there's a slightly greater deviation than we had before. But the idea here is we have one factor, and that is which personality category is the state put into. We have 3 options: the friendly and conventional, the relaxed and creative, or the temperamental and uninhibited. And depending on how we want to set up our null values, we can compare our observed frequencies, how many there are in each category, to what we might expect if the null hypothesis of random variation were true. And in both cases here, we find that we have a statistically significant deviation from that based on using the proportion test, or the chi-squared goodness of fit test in Jamovi. If you want to look at the association between 2 categorical or nominal variables, the most common choice is the chi-squared test of association, also called the chi-squared test of independence. And let me demonstrate how this works by starting with a split frequency. Let's come up here to exploration and descriptives, and let's look at, for instance, psych regions. This is in the state data set that I supplied. I'm going to put that here under variables, but let's split it by whether a state has a Republican or Democrat governor, because it's possible that there is some association between the political party of the governor and the state's personality as rated by some researchers. Now, right now, all it's telling us is that there are 48 cases in the data. I'm going to remove this extra information that I don't need. There we go. Now the table's a little bit smaller. I do want to get a frequency table. I'll click on that. And this is going to tell me how many people, or really how many states there are in each combination. And then I'll also ask for a bar plot at the same time. And what we have here is that we have 20 Republican governors of states that are considered friendly and conventional. We have 6 Democrat governors of states that are considered temperamental and uninhibited. And we can see that in the chart down here. Again, I apologize for the overlapping labels. I'm sure that'll be fixed in a later version. The blue lines are Democrats and the yellow gold ones are Republicans. And what you see is this huge spike in terms of friendly and conventional. The vast majority of those states have Republican governors, where the other ones appear to be somewhat split, a little more Republicans in the temperamental and uninhibited. But let's find out whether this difference is statistically significant, whether there is in fact a statistical association between the personality of the state and whether the governor is Democrat or Republican. So we'll use the chi-squared test of association for that. Let's come up here and go to frequencies. And then I come down here to independent samples. What that means is we have different groups of people in each of these categories, or different groups of states. And it's chi-squared test of association, also called the test for independence. And I'll click on that. And here's what it's going to ask me. I need to give it the rows and the columns for what's called a contingency table. That's just a table of rows and columns. So I'm going to start by putting psych region as the rows, and I'm going to put governor as the columns. That will mirror the table that I already created. And I could add extra layers, but that gets really complicated and hard to interpret. What that would mean, by the way, is putting in another categorical variable here. So we'd end up with a 3-dimensional table, but you don't want to deal with that. It's too hard. We have a choice for statistics. Chi-squared is just fine for what I have here. These ones, the comparative measures, including the confidence intervals, only apply when you have what's called a 2x2 table. And that means 2 rows and 2 columns. We have 3 rows and 2 columns, so these ones don't apply to what we're doing. We have some other choices. We can get a contingency coefficient or a phi and Kramer's V. Let's hit a contingency coefficient, and that's like a correlation coefficient here at the bottom. We can do some ordinal statistics. We have categorical data, not ordinal, so I'm going to leave that alone. And then we have some choices about what we put in the table. Now, right now, what we have are just observed frequencies, the number of states that fall into each combination. We can also put expected frequencies, and that's important because that's what the chi-squared test is comparing these observed values to. So for instance, up here in friendly and conventional, we have 4 states with Democrat governors. But if the data were completely randomly distributed, it would be 7.5. On the other hand, down here, we have 8 states that are temperamental and uninhibited and have Republican governor. But we would expect, if things were random, to have 9.63. The way it gets that, by the way, is by multiplying the column totals by the row totals and then dividing by the grand total for each of the cells. But the important part stays the same. Down here, we have our chi-squared test, and we get a value of chi-squared of 4.89. With 2 degrees of freedom, we have a probability value of 0.087. Now, that's something that's not very likely to happen by chance, but because it's greater than the standard cutoff of 0.05, we conclude that even with this really big difference right here, that these results are not statistically different from what we would expect through random variation. So even though it looks like there's a big difference, it doesn't hold up under null hypothesis testing. And that's one of the values of doing the chi-squared test. Even something that looks at eyeball level like a big result, when you do the actual numbers and get the inferential test, it may tell you a different story, which is exactly what happened in this situation. One of the things I really love about Jamovi is that they include some really unusual or specialty tests, but make them really easy to use. One of these is McNemar's test. And this is a test designed for contingency tables, but instead of being independent variables, it's for repeated measurements. Now, I have to admit, I've been doing research for 30 years and I've never had to do this. But it's always good to know that when you come up against this kind of question, you can get the right tool which gives you greater power and precision in your research. So McNemar's test is for categories, and it is for frequencies in those categories, but where the categories are repeated. Now, what I'm doing here is a little bit different. In my other examples, I've had 1 row per observation, and so I've had these long data sets. Right now, I'm using a summary table, and it's kind of nice that Jamovi lets you do this in a number of situations. That way, I can do it this way instead of having like 85 rows of data. The data that I'm using actually comes from a table that I saw on the Wikipedia article for McNemar's test. And it's about patients with Hodgkin's disease and whether they and their siblings had tonsillectomies. I don't know the association between the two, but it's an interesting example because the sibling goes with the patient. So there's a connection between the two of them. Let me show you how we set this up using McNemar's test in Jamovi. We come to frequencies and we come down right here. They call it McNemar test. If you go to Wikipedia's McNemar's possessive test. I'm going to click on that. And what we need to do is simply take our data, put in what variable has the row labels, what variable has the column labels, and then the variable that has the counts or the actual frequencies themselves. That's because I'm setting this up as a summary table. So I'm going to take patient and put that in rows. And you can see how it starts to fill it in right here. And I'm going to take sibling and put it into columns, and it fills in the table, but it doesn't have any values yet, except to say that in theory, there's just one of each. But then I take the n, that's a variable that tells you how many cases there are in each category, and I put that right here, and it fills in the table. And it does a couple of things. Number one, it gives us that there are 37 cases where the patient with Hodgkin's did not have a tonsillectomy, and neither did the sibling. But there are 26 where they both had tonsillectomies. And so there's an association in that way. We also have the actual result here. McNemar's test is based on the value of chi-squared, and it's interpreted in the same way that if the value of p, the probability value, or the probability of getting the observed effect size if the null hypothesis is true, is 0.088. Now, that doesn't meet the standard levels of statistical significance, but it's in the direction. I do want to show you a couple of other things we can do that can be really helpful. And that is anytime you're dealing with a table, and especially when you have samples of different sizes. Now, you see we have 44 Hodgkin's patients that did not have tonsillectomies and 41 that did. Those numbers are really close to each other, so they're easy to compare. But for the siblings, it's 52 and 33, and that makes the comparison a little more difficult. And so what you can do are get row and column percentages. Now, let's do just row percentages first. What this means is that for the patients that did not have a tonsillectomy, 84% of their siblings also did not have a tonsillectomy, whereas 16% did. So they add up to 100% going across, and that's going to be true all the way across. So this really just tells us that 61.2% of the siblings did not have tonsillectomies and 38.8% did. Independent of that, you can get column percentages. I'm going to turn off the row percentages for just a moment, and we'll get column percents. And now what this does is it adds up to 100% going down. And this is what's really nice when you have different overall frequencies. So we have just 52 people without tonsillectomies, 33 that did. And so we can say that of the siblings that did not have a tonsillectomy, 71.2% had patient siblings who did not, and 28.8% had patient siblings who did. And we can compare that to the percentages over here. And that allows us to make a sort of an apples to apples comparison, even though the total frequencies are different, because often you're more concerned about the rates. And that's something you can do with any kind of chi-squared table. You can do it in the binomial. You can do it in the chi-squared test for goodness of fit, for the chi-squared test of associations. That getting the percentages is often easier to interpret. And the same thing is true in McNemar's test, which allows you to do a contingency table for paired data. Another surprising but useful option in Jamovi for analyzing frequency data and associations between them is log linear regression. Now, what this is a form of regression where instead of trying to predict a person's score on a quantitative or continuous outcome variable, you're trying to predict the number of observations, the frequencies within cells of a contingency table. It's a powerful method, although it can be confusing to read the output. My goal here is simply to show you that it's easy to put these together in Jamovi. If you decide that this is something you need, then you're going to want to consult your other resources on how to design and how to interpret a log linear regression. But calculating it in Jamovi is very simple. Let's do this. Let's look at the association between two of the categorical variables in the state data. Let's look at psych regions where the 48 contiguous states of the United States are classified according to their personality characteristics, whether they're friendly and conventional, temperamental and uninhibited, or relaxed and creative. And then let's also look at whether that state currently has a Republican or Democrat governor. It's not the most compelling, but it's a useful comparison. What I'll do is I'll come here to frequencies and come down to this last option, which is log linear regression. When I get that, it asks me for what the factors are. Now, please note, it's not saying which one is the predictor and which one is the outcome, because the model really is kind of symmetrical. It doesn't matter. It's just trying to put together the entire table without necessarily saying this one causes that one. So what I'm going to do is I'm going here and get psych regions. I'll move that over. And then I'll also get governor. And I'll put that over. Because I have a table that gives one row per observation, I don't need to do the counts. But this is my initial results. Let me scroll this over a little bit. It's kind of a big table. But you can see, for instance, that we have an intercept at the top. I'll close this so we can look at the whole thing at once. You can see that what we have here are a collection of coefficients. This is like a regular regression. And we have the estimate, the actual predicted value for that coefficient, its standard error, the z-score, which is this one divided by that one, and the p-value that goes along with it. Now, we aren't surprised that the intercept is significantly different from 0. The two for psych regions are not significant. Democrat versus Republican, we have a major effect there. And then we have a nearly significant interaction for these two regions, relaxed and creative versus friendly and conventional, by Republican versus Democrat, in terms of trying to reconstitute the frequencies within the table. Now let me click on this and let's look at a couple of our other options. By default, it gives us the one factor for psych regions, the other factor for governor, and the interaction, which is what we want. That gets us a more nuanced model, even when we're dealing with a really kind of small 3x2 table. In terms of the other options, we get to pick our reference levels. So let's say we can pick instead temperamental and uninhibited, and that's going to switch the way the table over here is displayed. And if we want to put Republican as the default value for governor, we can do that as well. And that's going to change the way that some of these values are calculated over here. So now you can see, for instance, we have this value up here, friendly and conventional versus temperamental and uninhibited. That's now statistically significant. And this value here that compares the two with Democrat and Republican, it's changed a little bit. So overall, it's going to give you the same values. It's just going to parse it out differently. You have several choices on how you evaluate model fit. We'll just leave it with the standard deviance and AIC, as well as McFadden's R-squared. Those show up here in the table at the top. Actually, I am going to add the overall model test. That's going to give us a few more columns here. That gives us a chi-squared test and allows us to do an inferential test for the entire model. And here we have a chi-squared value, and we can see that there's a significant deviation between the observed and the expected frequencies or predicted values. We can also come down and get some of these other values, say for instance, a confidence interval for the estimates, and that's going to add another 2 columns over here in case you want a little richer picture for the values you have. And then we can come down and we can get estimated marginal means. Now I find it handy to do these. This goes as charts. I'm going to add a new term and I'll do governor right here. I'll just click that in. And then that's going to give us marginal means plots. And this is probably the single best way to look at the results of the log linear regression, is to come down and see these in terms of the counts that we get for psych regions along with their confidence intervals and the confidence intervals for the governor. And so there's more that you can do with this. There are some important distinctions to be made when conducting a log linear regression. But the amazing thing is that Jamovi includes this, that it's an option for a free, open source, and user-friendly program. And so depending on the nature of your data, you could do either the chi-squared test of association or independence, or you could do something a little more sophisticated with the log linear regression. And the great thing is that the Jamovi gives you the choice of one or the other. Our next topic in Jamovi is factors. And the idea here is that really, data is a jungle and it can be confusing and it can be overwhelming. And truthfully, sometimes less is more. Specifically with data, what that means is going from 1,000 variables to maybe a dozen or two that you need to deal with, it's much easier to find the order and meaning in that. You also tend to have more reliable and stable measurements. And the first procedure we'll look at in Jamovi is reliability analysis, because sometimes you want to talk about the flock, the whole, and not each individual sheep. Perhaps you want to combine the variables you need to get a single scale score. But to do that, you first need to make sure that you're dealing with similar variables, that they're measuring similar things. And reliability analysis, whether with Chromebox Alpha or McDonald's Omega, can allow you to do that. Or if you're trying to find the main dimensions that make up your data, like finding the main streets in a city, you can try principal component analysis or the closely related exploratory factor analysis, which, while being based on different mathematics and a different theory about the relationship between observed variables and implicit factors, accomplishes basically the same thing. And both of these approaches are exceptionally easy to set up and interpret in Jamovi. Or maybe you already know the bins that you want the variables to go into. And in that case, you can use confirmatory factor analysis, where you put together the factors that the variables go into and the observed variables, and you see how well the variables match up with those factors and how well your model explains the covariance in your data. But whichever technique you use, it'll help you get some clarity in your data so you can start on the path towards insight and action. In design, you'll hear the saying, less is more, and the same thing is true to a certain extent in data analysis. Instead of trying to analyze 50 different variables, why don't you collapse them into a smaller number of more manageable variables? That's going to give you more reliable information and more stable insights. But in order to do this, you need to first establish that you can collapse the data, that there are correlations that you're trying to combine like with like. And the most common way of doing this is with a reliability analysis, which looks at the relationship of several variables that you would like to combine. This is very common if you're working with survey data and you're asking several questions about the same general concept or construct. In this data set, which is based on real data on the big 5 personality factors, now we've talked about those before because Jamovi has a built-in data set, but it had the summary data, or rather it was already collapsed. This is a data set that has the 10 questions for each of the 5 scales: extroversion, agreeableness, openness to experience, conscientiousness, neuroticism. And so we've got 50 personality variables here. And this is originally from an open source data set that has nearly 20,000 cases. In the downloads for this chapter, there's a folder called Big 5. It gives the references and the notes for this data set. What I've done is I have a randomly selected 1,000 cases that we're going to work with to demonstrate reliability and really the scale functions of Jamovi. So let's start with this. We're going to just see what we have here. We have a data set with an ID numbers. That's just a row ID that I put in there. The age of the respondent, their reported gender, and then we have a whole bunch of questions that they rated themselves on. And the data information that you can download contains a description of what each of these questions were, but they're all rated on a 1 to 5 response scale. And the numbers up here, for instance, N4, N5, mean this is the neuroticism 4th question, neuroticism 5th question, and so on. There's A for agreeableness, C for conscientiousness, and O for openness. And that gets us to our last one. So there's 10 variables on each, and we want to see if we can combine them. And so we're going to come up here to factor. Now, factor is an umbrella term because all of these procedures have a lot in common. They all have to do with fundamentally whether there is correlation or covariance between the variables that you're looking at. But we're going to start with this one, scale analysis. A scale meaning a questionnaire or a survey where you have multiple questions designed to measure or scale the same thing. So we'll hit reliability analysis. And here are our options. It simply asks us what the items or what the questions are that are supposed to go into the same scale that are fundamentally measuring the same thing. Now, the nice thing is this information we have is already labeled E1 through E10. These are 10 questions that are designed to measure extroversion as opposed to introversion. So let's just take those 10 and move them over. So when we run the reliability analysis, this is our default table, and it gives us something called Chromebox alpha. That's a lowercase Greek alpha or a. And it's like a correlation coefficient. And what you're hoping for here is to have a positive value that is close to 1, maybe 0.7 or higher. We have a negative value, which is really bad, and it's a low value. This is happening because we've got some funny things going on with the data. But that is something we're going to be able to fix. But let's do a couple of things really quickly. I want to come back to these scale statistics, and I want to click mean, and I want to click standard deviation. Now, right now we have a mean that's really close to 3. That's on a 1 to 5 scale. That's going to be the midpoint. So that's great. Standard deviation, there it is. I find it really helpful to come over here and do item statistics and get the Chromebox alpha if the item is dropped. So we've got 10 items in this scale. What it's going to do on each of these is say, well, if you got rid of that one and kept the other 9, what would it be? And you see it bounces around, but it's always negative. But a graphic can also be really handy here. Let's click on this one, correlation heat map. It's kind of a cute thing, especially when you have positive and negative correlations. We're going to scroll down here. And in a second, the correlation heat map will pop up. What happens is when a correlation is negative, it shows up as red. When it's positive, it shows up as green. And we got this nice little checkerboard pattern. And the reason that's happening is exactly what our analysis told us here. It says it looks like 5 of these variables are reverse scaled. That's something that you do occasionally when you're doing surveys to make sure people are paying attention. You flip it around. And if we were in SPSS or some other program, we would then have to go and manually reverse variables and do this all over again. But fortunately, the package that this is based on, the psych package in R, makes it really easy to do this. All we have to do is scroll down here and tell it which ones are reversed. And it tells us right here, E2, 4, 6, 8, 10. So I'm going to go 2, 4, I'm just double clicking 6, 8, and 10. And look what happens over here. It's going to recalculate the alpha for this scale. And now it's recalculated this scale. And you can see, for instance, that we've got these little A's here to indicate that these variables have been reverse scaled. And look what's happened. The Chromebox alpha has gone from a negative 2 point something to a positive 0.89. And you can tell that dropping one of these variables, that's not going to help it overall. This is a very tight group of variables. Let's come down and look at the heat map now. It's all green. Everything's correlated with everything. And that lets us know that we are now safe to average these 10 variables. And so instead of having 10 variables that measure extroversion, we can combine them and get a single scale score that gets a more reliable and stable measure of extroversion. And of course, this is for the first of 5 major personality factors. This is extroversion. There are several others. And we would simply repeat this analysis for each of them as we go down. But the general concept is the same. We pick the variables we want. It calculates Chromebox alpha, which is like an average correlation between the items. It lets us know if any of them need to be reverse coded. It's very easy to set that up in the menus. And then we can see how each item contributes or if it seems to be pulling away. And in this case, the numbers support the whole thing and the graphical representation supports the whole thing too. We have consistent data, we can average it, and then we can have the less is more. Fewer variables, but more reliable and potentially more meaningful data to work with in our other analyses. When you have a novel data set, either because you created your own questions and you got your own data, or you're combining things that you don't really know if they've been put together before, one of the big questions is how can you combine things, or what is the emergent structure of the data that you have? One of the most common ways of assessing this is with something called a principal component analysis. There's also the very closely related exploratory factor analysis, which we'll cover in another video. Principal component analysis works on the principle of covariance, which is closely related to correlation. Right now, we've got a data set here that is on the big 5 personality factors. It's included in the data that you downloaded from datalab.cc, and it addresses extroversion and openness and conscientiousness and so on. And the question is, how well do they go together? And what is the structure that shows up empirically in the data? We know how they're supposed to go together, but what actually appears in the data that we have? Well, let's come up here to Factor and click on Principal Component Analysis. And what we need to do is first feed it the variables that we want. It needs ordinal or scaled or quantitative or continuous variables. So let's come here to E1 and let's go way down here to O10. By the way, you'll notice that these all have the three little circles that indicate that they are a nominal or categorical variable. But Jamovi is smart enough to know that they're really can be treated as scaled variables. They're from a 1 to 5 response scale. I'm going to just click to put them over here. And it starts giving us the results immediately. Now, it might take a minute to get it all the way through. And what we have here is similar to, think about correlations. There's an analogy here where we have numbers that go from -1 to +1, where the middle value of 0 indicates no linear relationship. And this is breaking it down into several components, several factors, ways of grouping the variables. Based on the data, it decided that 7 components seemed like the right answer. Now, we know that based on that, there's supposed to be 5. But this lets us know what shows up according to the settings we have in the analysis. Now, what's nice is right now it's organizing the 10 extroversion items together. The fact that some of these are negative and some are positive, that's irrelevant. It's the absolute value of the coefficient that matters. And you can see that neuroticism, all 10 are together. Same thing for agreeableness and conscientiousness. And things start to fall apart a little bit here with openness. I can actually tell you that based on the research, openness is generally the least coherent or the least cohesive of the factors. So this is not too surprising. But we have a few options. Number one is if you know about principal component or exploratory factor analysis, you have the option of rotating the answer. That's a complex thing, but what it does is it can make the results a little easier to interpret. Now, Varimax is one that's common by default, but I actually prefer Promax, which allows you to have what are called oblique factors, where they can be correlated with each other. They don't have to be all right angles in the multidimensional chart. So I'm going to change that to Promax. You can see it's saying we got Promax down here now. There's a few other things I'm going to do. One is I can hide the loadings. You see how we have a lot of blank space here? There's actually numbers on all of these, but most of the numbers are really small. And what Jamovi does is it covers up the ones that are low. Now, let me show you. If I were to change it to like 0.5, then it's going to redo the table and it's going to hide a lot of the stuff. You wouldn't usually put a number that big, but it makes it easier to read the table when you hide the low values. There's a few other things we can do. Now you see, for instance, it deleted this one. And on the other hand, we're losing almost all the other values that are off to the other sides. I'm going to put it back to the 0.3 where it was. But what I'm also going to do is I'm going to look at the assumptions here. Now, one important assumption in principal component analysis is something called sphericity. And you can think of it as sort of an analog to normality. And we just need to run through that and see how well we load. Now, we've got a Bartlett's test of sphericity, and it lets us know that our data seem to differ significantly from the null hypothesis. And you need to take that into consideration when you are interpreting the results of your principal component analysis. But let's do a few other things. Let's do a component summary. That's going to give us some statistics for those components. I'm also going to ask for component correlations and get a chart that's called a scree plot. It's going to take a moment for those all to load up. What the component statistics tell us is how much variance in the total data set can be accounted for by each of these components. Now there's 50 variables, so there's basically like 50 units of variance to account for. And the first one accounts for more, and they drop down as it goes through. You can also see how the components are correlated with each other. If we use what's called an orthogonal rotation, then it forces things into right angles. We wouldn't have any correlations at all. And there's our test of sphericity. This one down here at the bottom, the eigenvalues, those are the values that correspond roughly to how much variance each of our components accounts for. And it's called a scree plot, by the way, because scree is the rubble that's on the side of a cliff, and it's a little bit like what we have building up right here. And we have 50 components because we have 50 variables. So we have 50 potential components. And the real question is, how many do you want to use? And there are several different rules. One rule right here is to only keep components with an eigenvalue. That's this thing that talks about how much variance each of these components accounts for. Maybe an eigenvalue greater than 1. You can do that. What we have right here is called a parallel analysis. That's shown by these yellow dots. That's where it looks at a random structure and tries to see if we have something better than what's random. There's also what's called the elbow test, where you look at where things curve. And because I happen to know that there are 5 factors supposed to be in this, I'm actually going to come here to fixed factor, and I'm going to hit 5. And when I do that, we're going to get a very different factor structure that actually should correspond very closely with what's intended with the data, where we have 10 variables on each of 5 different factors. We'll wait a second for that to load up. We've lost the one reference line here, so this plot's exactly the same, just without the line we had before. But let's come up to here. And now you see that the component structure is much clearer all the way down to openness, where we can see those 10 items that are supposed to go together are in fact here together. Now, this is probably one of the most important things you need to do when you're analyzing survey data or a number of variables that might potentially be correlated with each other. A principal component analysis is going to allow you to determine the underlying structure and see what you can combine with each other to simplify the data that you have to deal with and hopefully have more reliable information at the same time. Sometimes when you're analyzing data, you have to draw distinctions that don't make much of a difference. And one of those distinctions is between principal component analysis and exploratory factor analysis. Now, these are based on profoundly different mathematics, and they also have a different philosophy about the relationship between the individual items that you got data from people and the implied or implicit factor behind them. But the fact is, they look really, really similar, and people use them to do the same things. And there's so much commonality that it's sometimes hard to remember which one you're doing. I've showed you how to do principal component analysis. I'm now going to show you how to do the same kind of looking for structure with exploratory factor analysis, and you'll see that it looks very similar. What I have here is Big 5 data that's included in the folder that you downloaded from datalab.cc. I'm going to come up here to factor and go to exploratory factor analysis. And mostly it's the same. I pick all the variables that I want to use in my factor analysis. This is my 50 variables that people use to assess the Big 5 personality factors. I put them over here, and you can see it's crunching away already. I'm going to change my rotation from Oblomin to Promax. I can also do Bartlett's test of sphericity, which is one of the assumption checks. I can ask for a factor summary, factor correlations, and a scree plot as well. Truthfully, the major difference here is that the second factor is up on top and the order is a little different. Otherwise, it came up with 7 factors. When we did PCA, we had 7 components, and they're sprinkled around a little bit differently, but it's basically the same result. This is our openness factor right here, and things are scattered a little bit for this last item. But if you come down here, you'll see that the factors also have approximately the same amount of variance they go through. The correlations are going to be similar. The scree plot looks nearly identical. And in fact, I'm going to do 2 things. And in fact, I'm going to do one thing here, and that's because based on the scree plot and based on what I know about this data, I think a fixed number of factors, 5, and you see it actually is calling them components even though we're doing factor analysis, might be a little more useful for what we're doing. Now that I've done that, you can see we have just 5 factors that are correlated. And now things are lining up much more neatly. But fundamentally, we're getting the same results that we had with the PCA analysis, principal component analysis. And so take your pick, one or the other. I generally do principal component because I prefer that it starts with the individual variables and then infers something about a factor that goes to them, as opposed to the idea that the factor is first and it leads to the individual variables. But fundamentally, they're going to accomplish the same thing. They're going to help you find which of your variables go with the others and give you the option of then combining them to get more stable, reliable data and a smaller number of variables that you have to deal with when you're doing your analyses. Either one of these will help you find the sense and the commonalities in your data and help you improve your analysis. One of the most amazing things about Jamovi is that this free, simple, friendly, open source analysis package includes some incredibly high-end analyses. In fact, the most surprising one for me is the inclusion of confirmatory factor analysis, something that, for instance, not even possible to do in SPSS if you're on a Macintosh. And if you're doing it in other programs, it gets really, really complicated really fast. And this is by far the easiest and fastest and cheapest way to do a very sophisticated procedure. What confirmatory factor analysis, or CFA, is an attempt to take data and say, we know how the data is supposed to combine. We know that these 10 variables should go to this factor. These 10 should go to this other factor. And it allows you to specify those factors and see how well your data fit your hypothesized factor structure. It also allows you, by the way, to compare the fit of factor structures across two different samples. That's a different thing, but let's go and take a look at how to set up a confirmatory factor analysis in Jamovi. We come to factor and we come down here to confirmatory factor analysis. Now, I am working with the Big 5 data set that you can download from the sample files on datalab.cc. And what I have are 50 different variables with 10 each for the 5 different Big 5 personality factors: extroversion, agreeableness, openness, and so on. And what we have to do is we have to tell Jamovi which variables go together and what the name of that factor should be. So for instance, E1 through 10 come first. I need to come here and say that that is extroversion. So I just click on it and type that. Then I come and select these 10, and you can see the names have highlighted over here. And I put them in right there. After that are N1 through 10, which is for neuroticism. So I'm now going to add a new factor. We scroll down a little. We'll see if I can spell neuroticism correctly. And we select the 10 variables and put them into neuroticism. There they go. We're going to add another factor because there's 5 total. And this one is agreeableness. I'll select those variables, put them in. After that is C, which is for conscientiousness. Let's scroll down here. Conscientiousness. I think I got that right. C1 through 10, feed those over. And then the last factor is O for openness. Come down to the bottom and type in openness and put those 10 in. And now we've specified the important part of our confirmatory factor analysis. We've told Jamovi we've got 5 different factors. We said what the names are, and we said which variables go with which. What's interesting is we don't even have to tell it which ones are positively associated, which ones are negative. We don't have to look at the reverse scaled items. It's going to be crunching away on this for a little while because this is a pretty mathematics intensive option. But let's take a look at a few other things we can do. Now, if we had specific other variables that contain what are called residual covariances, things that don't necessarily go into the factor but help explain some of the leftovers, we could specify those. And what you do is you would say, you take this one variable and then you specify another one for the residual covariance. We don't have that, so I'm going to ignore that. Under options, we can change how we deal with missing values. We only have a very small number of missing values. I'm just going to leave it like this. We can do constraint factor variances equal 1. That sounds good. Under estimates, we can look at a few different ways of calculating results. I'm going to do a standardized estimate right here. I'll close that. Under model fit, we have several choices. CFI stands for Comparative Fit Index. TLI is for the Tucker-Lewis Index. RMSEA is for Root Mean Square Error of Approximation. And this over here is a chi-squared test. We've seen that in several other places. I'm going to leave those defaults right there. And then the additional output, we've got a couple of really nice things. One is the residual observed correlation matrix, because what Jamovi is going to do is it's trying to reconstitute a correlation matrix based on what I said, how the variables went together. And so I'm going to ask for that. And it's also going to highlight any residual values that are greater than 0.1. It's going to say, this is where the model is off more than in other places. And then finally, I'm going to ask for a path diagram. And then we'll just wait a minute for Jamovi to finish crunching all the data and see what it has for us. I actually paused the recording for a minute because it takes a while to get through all this calculation. But here's what we have. We have our factor loadings where we said extroversion is the first factor and the indicator is the name of the variable that we say goes into that factor. The estimates are like regression coefficients, and they say multiply this number against the variable to get the factor loading. We have standard error, z-scores, the p-value, and by the way, you can see that everything here is highly significant. And then finally, the standardized estimate, again, like a z-score, and that's a good way of assessing the relative contribution of the variables. We have the same thing for neuroticism, agreeableness, conscientiousness, openness, and we got a lot of numbers there. We come down to the factor estimates. It parses it up a little bit differently, where it's looking at the connection between the factors in terms of extroversion as a function of these other things. The model fit's an important one. This is where we have things, again, the comparative fit index and so on. But I like these two things at the end. I'm going to close this so I can make a little more space on the screen and open this up. I'm not going to be able to get the whole thing. This is a really, really big correlation matrix. These are correlations, again, from -1, which means a perfect negative linear association, to 0, which means no linear association, to +1, which is a perfect positive association. And this correlation matrix is reconstituted based on the way that we said the variables went together. And these are residuals, which means compared to the actual correlations, which it computed in the background, this is how far off our reconstituted matrix is. The important things here are the ones in red, and that says we're off a little bit on that combination of variables. And I can scroll down. You can see this thing's really kind of huge. And so you can take that as an indication of how close or how far away you are. If you want to go back to the fit indices, I can tell you that these numbers indicate that our fit is adequate. It's kind of okay. It's nothing spectacular, but it looks like we're not too far off. Maybe we would want to see which variables are loading best, which ones seem to be contributing the most to the fit, but we may have a go ahead here in terms of confirming the structure that we think we have. And then the last thing is the path diagram. And it's not putting the coefficients on this, but it simply says, these are the associations. We say that we have 5 major factors: extroversion, neuroticism, agreeableness, conscientiousness, and openness to experience. And it says that we have all of them associated with each other and that each of them feeds into its own 10 variables. And so that is, in a nutshell, this is the basic functionality of confirmatory factor analysis. Again, a very sophisticated procedure that a lot of programs don't let you do at all. And it's one of the really a special present from Jamovi that it makes it possible to do this. You're going to have to do more research on how it all works and how to interpret the results. But the fact that you have a tool that can do it and that does it so easily is a huge boon to researchers everywhere. So now we've come to the end of our introduction to Jamovi, and it's time to talk a little bit about both what we've accomplished and what you might want to do next, your next steps. First off, here's what we've learned. We learned about installing Jamovi and sharing files and wrangling data, exploring data, visualizations, t-tests, analysis of variance, regression models, analyzing frequencies, and finding factors. We've learned how to do almost everything that's necessary for the vast majority of data projects. And really, I just need to know, have you learned how to use spreadsheets before? Do you know how to use either Excel or Google Sheets? Because if you know how to use spreadsheets and if you've learned how to use Jamovi, then tool-wise, maybe you're there now. Maybe you have what you need. I'm firmly of the belief that spreadsheets and Jamovi cover the analytic necessities for the vast majority of people who work with data. Now, it's possible that you might need some more tools depending on the kind of work you do, but not everybody needs it. If you're going to do something that is more advanced than what Jamovi does, and Jamovi's got a lot of capability, then you might need to do some programming for data analysis. And that usually means either R, the statistical programming language R, or Python with the collection of data packages that are available for it. Those two are very, very popular in data science. And I like to use R a lot, but I much prefer working with Jamovi for the vast majority of my analyses. There are other helpful tools if you're looking for something to add to your toolkit. First, there's SQL, Structured Query Language, for data access, data manipulation, data cleaning. If you're working in an organizational setting, then SQL can be really, really helpful. And truthfully, you only have to learn about 20 commands to get most of what you need out of SQL. Second is Tableau is a proprietary desktop application. Now there's Tableau Public, which is free, but all the work you do is available free on the internet for everybody. And there's Tableau Desktop, which if you're a regular person or if you're a company is extraordinarily expensive. If you work for a nonprofit, you can get it for free. Tableau really is the tool of choice for interactive visualization, even for data scientists who are handy with code. And then third, presentation software. Because remember, you do all this analysis, you're going to have to communicate it to somebody. You're going to have to share it with them. And knowing how to use Microsoft PowerPoint or Apple Keynote or Google Slides is going to go a very long way in terms of making your work professionally meaningful. Now, you may have seen this chart before. If you're coming from the world of data science, you've seen this. It's called the data science Venn diagram, and it was created by Drew Conway several years ago. And he said that data science consists of 3 different fields put together. At the top left is coding. That's working with computers. At the top right is stats and statistics and mathematics. And at the bottom is domain knowledge. You actually have to understand the field that you're working in. And when you take the 3 of those and combine them, then you get data science. And it applies to a certain extent with what we're doing, even in this Jamovi situation. We've been talking about the tool. That's going to be that red circle on the top left. We have not talked very much about the statistics. That's the conceptual elements, nor the domain. That's the application. And so even if you have the greatest tool set in the world, there are these other areas that do need your attention. And so I would say probably the single most important thing is data fluency. And seriously, reading a bar chart and a line chart is, if you know how to ask a meaningful question and know how to read even these very simple analyses to get something that is insightful and actionable out of it, you're going to have huge value in what you do. I actually believe that bar charts and line charts and scatter plots probably cover 98% of the data visualization needs for most people. The simple tools are often the most effective. So one of the reasons I really like Jamovi, even though it allows you to do some complex things, but data fluency. And so here at Data Lab, we're developing courses to teach data fluency, the concepts and the principles that the tools help you with, but the tools are not a substitute for them. And of course, separate from the principles and the tools is the ability to work in a particular setting. So much of the real work in any data project is not the actual working with the numbers, but is in talking with people to understand what you're trying to accomplish and seeing how you can make sense of it and what to do with it. And the best way to do this is to work together with other people on real data projects to answer real questions. You can do that at your current job. You can do it with a volunteer group. You can do some online freelancing. Any of these are great ways to get the experience you need. Jamovi is an excellent data tool, but you need to have some understanding of the statistical concepts, the data fluency, and more than anything, the ability to apply it when working with real people on real settings. So, we've been talking about a tool, and you have these other possibilities that we talk about at Data Lab as well. But take them together. Take them together, and really, you're good to go. You've got what you need. I'm so glad you joined me here. I'm thrilled to show you Jamovi, one of my favorite new tools, and I really hope that you will start finding really interesting and exciting ways to use these and getting insight out of the data that you're working with and doing something amazing with it.